Good morning, everyone. Here we are once again back at it, hammer and tongs. I hope you all had a restful, nice evening. It's my pleasure to kick off the session. Before I do, I just wanted to comment. Some people mentioned yesterday, if you were in the back there, you couldn't hear very well. Now, usually in my meetings, people are yelling and screaming at each other, so there's no problem. The auditory, but here people like to whisper their talks, and so the microphone, so you'll be able to hopefully hear much better today. So my apologies about that, but anyway, I'm very happy to introduce Professor Valerio Virani. He is at the National University of Singapore. He was born in Milano in 1972 and graduated from École Polytechnique in Lausanne in 1996. Received his doctorate from that institution in 2000. Then he moved to the University of Geneva. We were both postdocs at the same time. I was in the group of Nicolas Gizem, the University of Geneva in Switzerland, where he was working on quantum information science and notably cryptography and Bell non-locality. In 2007, he joined the National University of Singapore as a member of the physics department. And he's an expert in quantum information, quantum optics, and we're very happy to talk about Bell non-locality at the bare minimum.
Thank you, Andrew. Yes, so well, I'm very happy to be here. Very pleasant conference, very congenial atmosphere. Yeah, so let's see if this thing works, by the way. Okay, so yeah, in terms of research, I run a small or not so small, theory operation in the National University of Singapore Center for Quantum Technologies. Very East Asian, of course you don't recognize, neither would I, but I mean you have an Indonesian, Singaporeans, Chinese, Vietnamese, Malaysian, Korean, Dutch, and myself. We're a very, very international team, and my students are going with AI, so they did this kind of things when we the group photo, which is much better than the original, at least the setting. Okay, so for the quantum part of this conference, I got it covered. Now for the classical philosophy and Catholic theology, honestly, my record is a bit dismal. Some years ago, just for fun, I tried to read if Thomas Aquinas had something to say about randomness and uncertainty. I found something, I wrote something. My physics colleagues were quite excited. My Thomist colleagues told me that typical constructive feedback, that I got nothing right. I mean, still, I think that it would be an interesting question in general to which of the classical philosophers, classical even back, right, had the idea that nature might be underdetermined. Apart from the swerving or Leucippus and some things in Aristotle physics that Thomas picked up, I'm not aware of much, but again, I'm not a historian of philosophy. I don't know if Plato, for instance, would have considered that there is some indeterminacy in nature. And then, well, occasionally, I don't know if it's a very virtuous or actually sinful. I use Catholic language to sell my papers, but this is actually a paper on physics. Okay, so this is really, and the sins are actually mistakes. But if you write sins and you phrase in terms of commandments, and in fact, this paper was more noticed because nowadays you have to do that because every day in the archive there are 100 papers. So unless you put some twist on it, nobody notices what you write. Anyway, that's pretty much my record about those topics. So today we are going to speak of Bell non-locality, a summary of Bell theorem. Every mechanism that explains the origin of all quantum correlations, of how quantum correlations arise, must be non-local. Let me spell it out for you. Quantum correlations, first of all, we are speaking of correlations between the outcome of measurements on two or more. I will stick to two, but you can do more. Suitably prepared quantum systems. Entangled, as the jargon goes. So that's the context, right? We are considering two or more quantum systems, not just one. And you make measurements on them, and you see that these measurements are correlated in a particular way. Non-local means that it seems that some knowledge of the measurement undergone by the other objects is needed, even if they are far apart in space, the measurements, and almost simultaneous in time. which is a way of saying that a signal slower than light would not arrive on time to carry this information. Now, every mechanism, this is quite important. I mean, at least, I don't know the background of all of you. So some of you may know these things very well. Some others may have heard confusing statements. Every mechanism, so be it deterministically or intrinsically random. So it's not that one, so you could think that the measurement or the outcome of a measurement is chosen by a really random process, intrinsically random. But nonetheless, that random process must be non-local. Just randomness without non-locality would not violate Bell inequality. It would just mess up the correlations, actually. Right? So that's kind of, and that mechanism, of course, in this context, it's easy to say, but I mean, we should be asking the question how nature does it. Because quantum theory predicts those correlations. So this is making something that probably all of you know, right? But I should be clear here. We're not speaking of mysteries. We're not speaking of dark matter, something we have no clue about, not even how to describe, right? Quantum physics does predict exactly those correlations. It just does not describe how they come about, okay? So that's the context. The basic experimental design looks like this. Sorry for the experimental, yes?
Well, this was the definition, this was the statement in Bell's paper.
No, that's my summary of it.
That's yours.
But don't forget that we are more than 50 years, almost 60 years out of Bell's theory, and we have understood something. In Bell's, I'm not the kind of historian of science that says, what were Einstein and Bohr discussing? I don't care. What I care about what nature is doing, okay? Sorry for the historians of science in the room. It might be very inspiring, but maybe neither Bohr nor Einstein nor anybody at that time had the correct view, okay? And in particular, Bell might have had a non-correct view of what he was doing, and I don't care. Okay? Okay, so that's the type of experiment you might find. Probably if you go to the lab of Abraham, you find something like that. Maybe you can even visit it later. So you have a source there producing these particles that go somewhere. There's a measurement device. You have to choose the measurement, as was emphasized yesterday by Vincenzo, and you get an outcome. You see some result in the... Okay, that's a standard experimental setting. This prepared entanglement. I want to say the one thing that entanglement is a word from the theory, as Paolo left it clear yesterday. So the precise statement would be that the source prepares a system in a state that is described as entanglement in quantum, as entangled in quantum theory. I can't just say, oh, these two things are entangled. For me, that sentence doesn't make sense, or is a shortcut. Okay, these two things are in a state that, according to what we write down today as quantum theory, look in first quantization and looks entangled, or is entangled mathematically, right? So for me, entangled is a mathematical statement. I am not entangled with anything, but my state might be described as an entangled state with some other things. Now, in practice, any pair of quantum systems would do. In practice, photons are ideal because they travel at a long distance. They have no charge, no mass, so don't interact with pretty much anything. At worst, they are lost by scattering. So that's the setting of most Bell tests. And in fact, all the early experiments, the Clauser-Spitz, Eilinger-Gisin, everything, until the year 2000 something, and also in the loophole-free experiments of Vienna and NIST, were using this scheme. There is a rising different scheme, that's the event-ready experimental design that maybe some of you are less familiar with. So the idea is that there is first a preparation stage and then the measurement stage. In the preparation stage, there are two atoms. I will skip the details, but there are two atoms. They can be real atoms or can be superconducting qubits or artificial atoms or NV centers, so some energy levels in diamonds. So these guys do something and emit photons. Again, exactly how. So the experimentalist triggers the emission of a photon by these atoms. These photons at the center are measured in a particular way that entangles them. And by doing that, you entangle the atoms. It's called entanglement swapping. So now that's the preparation. So now the two atoms are entangled. And you can wait a few seconds or a few microseconds or whatever and measure them. Okay, so it's like the different, so it's not just sending the two and preparing the entanglement locally and sending it out, is preparing entanglement at a distance and then measuring. What's the advantage? The advantage is here, you still send photons. They don't interact, so they travel far. But atoms are much easier to detect. The efficiency of detections is much higher. So you close what is called the detection loophole in this case, in a much simpler way, which is one of the typical problems in some of the Bell tests. Okay, so these are the ways the experiments are done. And these have been used approximately in 2015. The Delft experiment NV centers, Munich, group of Weinfurter use rubidium atoms. And in Zurich, Wallraff has done it with superconducting qubits. Of course, in Zurich, they have money, so they could build a whole 40-meter superconducting line cool down. Not every university has those funds. Anyway, now one very, very, very important thing, right? I spoke of photons, atoms, and so on. The Bell test is device independent, which means that to design an experiment, you need to know a lot of physics. But to test it, so I can, in principle, go into Abraham's lab without even knowing what a photon is and so on, looking at, okay, they're choosing this measurement, they're getting these outcomes. I go to my piece of paper, I do the statistics, and I see that they're violating a Bell inequality. Without having to speak about photon, about atom, about spin, about rotational invariance, about any of these things. Okay, don't matter. They matter for the experiment, don't matter for the theorist. So that's the scheme of Bell test for a theorist. There is a source that actually doesn't matter at all. It doesn't matter that there is a source. It means that at some point you have to tell me, oh, that there is something in my device that I can measure. How it got there, not my problem. So you can even forget about the source, but I will need it for my talk. And then there is the random number generator or the human being or whatever, choosing the measurement and getting the outcome and seeing the outcome on the computer. So this is the device-independent idea. So for instance, if we have to explain how nature does it, we should not go into false tracks that use physics. I know it sounds strange. Let me repeat it. We should not go into false tracks that use physics. For instance, it's a photon. Photons, they propagate at the speed of light. Hard to understand. We don't care. By the way, it doesn't need to be a photon, as I said. Or it's a singlet state, so it must preserve the symmetry. We don't care. By the way, we can do Bell violations without singlet states, with the states that have no obvious symmetry in any sense of the elegance, right? So, yeah, it's about statistics.
Conditional probability.
Conditional probabilities, yes. Conditional, again, the conditional part is also a bit, because they don't have the same status, those X and Y, the measurement but yeah, you consider conditional probabilities. Okay, so John Bell famously wrote this thing, right? The scientific attitude is a correlations cry out for explanation. I presume explanation, what he had in mind is Reichenbach's principle. In his book, The Direction on Time, published 3 years after his death, Reichenbach wrote that there are 2 elementary processes for correlations. Well, it's kind of obvious once you think about it, but I don't know why he must be the first one who wrote it. Or maybe not. Maybe Thomas Aquinas had something to say about that. But, so there's a common cause and the direct causation. And of course, you can, a more complicated process may involve some of both, right? In all kinds of directions. So I said the Bell test looks like this in the lab. And so the obvious explanation is the common cause, right? Because, yeah, you see it there, right? There's no arrow that goes in those directions. So it seems it's a common cause. It's what we call local variables. Why local? Because it looks like the result of this measurement is only due to what comes in from the source and the details of the measurement apparatus. And this, for many years, was what people thought, right? That the quantum uncertainty comes from the fact that this poor little particle meets a huge apparatus full of atoms, 10 to the whatever. I mean, come on, some randomness must happen there. Well, too bad that's not the case, right? That's what Bell disproved. And disproved conclusively. So the local variable explanation is fully falsified. Now, we can discuss whether there is another pseudo-classical, pseudo-deterministic explanation, but not that one, okay? The violation of Bell inequalities falsifies completely the local variable approach. That's it. Okay, then some people that are smart said, oh, but this is quantum causality, so it's not, you see, there's a psi here, there's not a lambda, so it's a different type of causality, it's quantum and not classical. For me, again, quantum is a theory. So this is playing with words. In fact, as my mentor Nicolas Gézin said, it's causality in Hilbert space, not in space-time. And anyway, you cannot do it in space-time, so that's it. And by the way, a few years ago, they will not promote this paper too much, but this is the same people that do the quantum causal model, so it's not a different community. They just proved that actually, if you reason with the normative rules for these quantum causal models, you actually contradict quantum mechanics, right? So then, I mean, let's say that it's an interpretation or an approach to information propagation that is probably not very fruitful. You can go to Waterloo and discuss with them if you want. Okay, so then we need to add something. We need to add some direct causation. If we want to try to explain things in space-time, we need to add the direct causation, and the direct causation should go from the measurement to the outcome. Of course, it could go the other way around, right? There could be one from here to there. Again, this is important. What needs to be sent is really the input, the measurement information. So that it wouldn't work, trust me, to send here a message about the outcome. That can be fixed in other ways. And in fact, it probably doesn't work. So the input is what Bob's particle doesn't know about what happens on Alice's side. Yeah, and so that's a scheme we should be considering. And now, well, let's try to attempt a physics of this thing. Right? So what is that green arrow? What could it possibly be? Well, first of all, this is an unknown process, okay? We are in the realm of the unknown. No carriers of such information is known. If you think of the basic experiment, there is a photon going in, and the photon doesn't have anything that it can send faster or slower than light to another part. So we're not speaking of something that, yeah, sure, there is a neutrino or whatever. We have no idea what we're speaking about. That's important to keep in mind. The constraints that I'm going to discuss on the next slides is, first of all, the constraint about the content. So how much information should I send? And there's something called fine-tuning. You see, it's very obvious what it is, but it's not the same fine-tuning as the cosmological argument, anthropic, and whatever, right? It's a different fine-tuning. And then the constraints on the speed. And the speed, I will devote a few slides to that, and we'll discuss whether the speed of this influence is bound by the speed of light, or it can be faster than light. Okay, so the content. The question is, what is the information about X that I should send to B? Well, of course, you say everything, but that's always very safe, right? You send everything. And, still, the amount of information doesn't seem to be a big deal if you have also the common cause, if you have also the local variables. Otherwise, you need to send absolutely everything. For instance, for the 2-qubit state and any measurement, not just two measurements, any measurement, you can reproduce the quantum correlation of the singlet state or these kind of things by sending 1 bit of communication. Just one. That depends on the measurement. So it's a tricky model. You can play with it. There are different versions of it. But so it's not that you have to send a lot, right? Okay. Fine. Now, more problematic is the fine-tuning argument. It's kind of obvious, but apparently the first people who stressed it explicitly was Wood and Speckens in 2015. Is that, as you all know, probably I should have said it before, even if these correlations are at a distance or whatever not, if you stay on one side, there's no faster than light communication for us, right? So even if such a thing is happening, when you stay only on one side, you don't see you see all the same randomness. There's no signaling, right? It's only when you come together and discuss the measurement results that you see there were strange correlations. Strange, I mean, in the sense, right? So now, if I'm trying to communicate something and nothing gets conveyed, which I hope is not the case in this moment, it means that the communication must be scrambled in a very interesting way. Right? There is a communication going on and you scramble, but you don't just scramble it. You scramble in such a way that something arrives, because if you scramble it completely, nothing arrives and it's completely pointless. But you randomize in a way that we don't see it. You need a lot of fine-tuning for that. Right? So these are very constrained models, because again, I'm saying something, let's say to Vincenzo, but in a way that he can only understand, none of you can understand, right? So it means that really we should have some very fine-tuned agreement between us in order to, for you not to notice that I'm talking to him. Okay, what about the speed of influences? Well, the speed of influence, let's think first that because it's unknown, you can say whatever you want about that. And in particular, you can say that, okay, this influence can be there, but they should propagate slower than light. So they arrive, this diagram, for those who are not familiar, means that this influence arrives after any light signal that could come from. So, well, then you can say, oh, fantastic, then we can exclude these. That has been done since many years, right? It was closing the locality loophole, meaning that, as in the drawing, if the influence arrives after Bob has produced his measurement, well, too bad, right? It arrived too late, so the measurement outcome cannot depend on the influence. And so this is how every experiment since, well, Zeilinger 1998. I mean, Aspe 1982, 3 did something, then Zeilinger 1998, then all kind of people until the loophole-free bell test. It's how people close the locality loophole, is called. So locality loophole would mean that a signal propagating the speed of light could arrive to the measurement, right? Well, up to something, the power of Zeilinger, mediatic power of Zeilinger has managed to hide a few details, which is this. Provided you identify the relevant events. Example, we are speaking of something unknown. So when is the random choice made? Right? You have a device that says, oh, it's a random number generator. It's a box there in your lab, right? And say, no, I know when the signal comes out of that thing, and yeah. But which movement of the electrons led at that time to produce that signal? Maybe that movement of electrons started yesterday, in which case, right? So do you really know, because you're speaking of unknown physics, do you really know when the physics was put in motion that something new was really created? Only that we know is that the signal comes out at that time from the device. And that's the usual criterion used. Well, even worse, when is the measurement result classical? Do you have a collapse model? We don't. Some interpretation even say that it's never. So that thing can be arbitrarily far. So yeah, you can close the locality loophole if you identify the suitable events. If you don't close it. That's it. Now, however, now let's see what happens if I do make an assumption that the speed could be faster than light. And then there is a strange result that shows that these influences this is a theoretical result. It's not an experimental, is a feature of the physics. If you try to do the physics of these influences, you end up with this strange thing that in fact the influence can be hidden only if the speed of this influence is infinite, whatever that means in a relativistic setting. In fact, it doesn't mean anything in a relativistic setting, but so for finite v, any finite v, faster than light or slower than light, well, if it's faster than light, if the influence is faster than light, then faster than light communication among the participants, the human beings, would become possible. In some settings that have to be identified, so again, you have to identify the events. The criticism I was making before is still valid. You have to find the events. Even here it's worse. You have to find the preferred frame, that we also don't know what it is. But, okay, the argument uses 3 particles. You cannot do it 2. I can sketch it for later for those who are interested. So, in summary, if you want to explain quantum correlations with communication, faster than light or slower than light, so remember this, the physics of the influence is unknown. It may be very hard to check it experimentally, but the theory breaks what Shimoni called the peaceful coexistence. The theory of such influence would allow faster than light communication, in principle, in some situations, between the agents, unless it's infinite or faster. Faster meaning retrocausation, it goes backward in time. Okay. Another thing that people have discussed is the what we call measurement dependence, misleadingly called reduced free will. Misleadingly because there's nothing about human free will in any possible meaning that matters here. What matters is this. So whether there could be a possible overarching common cause that influences both the state preparation and the measurements choice, right? Because in no lab, because of speed, the measurement choice are made by humans, right? Really being there and pushing buttons with their own free will, even if that counts as free will, I have no idea. But you could imagine, since everything is a device, right? So there's a random number generator there. Well, you could think, I don't know, that maybe there is a fluctuation in the electric plug. They're all plugged in the same network, right? And that fluctuation influences the choice of the output of the random number generator and the way the state is prepared by the particle, right? In such a way that somehow they conspire. Of course, now if you have a diagram like this, there's a common cause for everything. You cannot falsify anything anymore, right? Because everything is determined here. Call it the Big Bang, but it doesn't need to be the Big Bang. It can be the fluctuation in the power grid of the city. Now here also, we have kind of good news, although this is a little bit more work in progress by those who care, I don't, is that there is very little leeway. So quantum correlations, suitable quantum correlation tested in a suitable way can beat such a model unless it's really deterministic. So if you say, oh, well, I mean, there is some correlation between the state and the measurement, but it's not absolutely deterministic, right? Well, then we can find some suitable quantum correlation in enough many measurements and suitable quantum states and so on, such that this explanation does not work, right? Such that even these correlations between the state and the measurements would not be enough to explain what you observe. Unless, again, this is fully determines everything, in which case, again, it's like the infinite speed and the other case. You're in a situation where you are stuck. You can't falsify anything anymore, super determinism. There are a few technical assumptions here that I think they're still open. Again, you can ask my friends. For instance, IID. There's an assumption that these models are independent and identically distributed. Usually you remove these assumptions by some hypothesis testing stuff, but this has been done for the normal Bell test. I don't think it's been done fully for this kind of models. But I mean, usually these things can be fixed up to putting your error bars a bit bigger or your p-values a bit smaller. Okay, so where do we stand with explanation in 3+1 space-time? Common cause alone? No, no, no. That's it. Common cause plus direct cause? No star. So my friend computer scientists put a star when they want to say there's an exception. Right? So no star means yes, if the speed is infinite or faster and with a lot of fine-tuning. Okay, so yeah, you can still believe this. By the way, Bobian mechanics would be exactly that. I mean, exactly that would be matched to that. So Bobian mechanics, of course, is not falsified in this case. Measurement dependence, again, no star. Yes, if it's full determinism. Yeah, if you have a full deterministic basic cause, you cannot do anything. So it's pretty dismal, right? What we can do in 3+1 spacetime is very constrained. Let me cite a atomistic text of a few years ago, but citing older papers. So as to the objection to causality from the Bell inequality, it sometimes suggested one could respond to it by, and I added the bullets to simplify the writing, denying that causal influence never travels faster than light, which is a very complicated way of saying, assuming that causal influence can travel faster than light, a double negation, just to make it easier to read. Or by allowing for either backward causation or an absolute reference frame, or positing a law to the effect that correlations in question take place. Okay, my comment on this is, okay, so this person could not know in the year 2000 that in 2012 we proved that only infinite speed works.
Unless there's backward causation.
Huh?
Unless there's backward causation.
Backward causation or faster, so that's only infinite speed or faster. So this one remains. This one must be infinite speed. Well, again, this one you can, well, yeah, if you go faster than light, I don't know why this is supposed to be different, because if you go faster than light, you better have an absolute reference frame, otherwise, or some ways of define excluding some, I mean, singling out some reference frames. This one, honestly, I have no idea what that means. but we could look probably outside free-flowing space-time. That's probably what it means, right? That there is some other, yeah. So let's look outside a bit. Let me just summarize and then. So the phenomenon we discussed is correlations predicted by quantum theory and observed to a high degree of precision. I mean, people like to say that because of the implication of these things, the Bell tests and this correlation have been tested like nothing else in science. Right? You say, no, the magnetic moment of a muon is whatever it is, right? Probably that's been measured 5 times. The Bell test has been done in all possible configurations. People keep doing them. Right? So I don't think there is any doubt. We're not referring to 1 or 2 things, right? Spain 1982 in his lab in Orsay. No. The question is, of course, how nature does it, and explanation by common cause is excluded, by direct causation is very severely constrained, measurement dependence also very severely constrained. So where does this leave us? Okay, so, well, yeah, you can look for explanation outside space-time. For me as a physicist, I would love to see an explanation that solves some problem, right? Because you can say, well, there is another dimension that encodes quantum information. So for instance, entangled particles, although they go far away from each other, they are still nearby to each other in this 5th dimension, right? And so they talk to each other in that dimension. That's no problem. I don't know how we would explain entanglement swapping in that scenario because those 2 atoms were never close. Suddenly they become close. But again, you have a 5th dimensional kind of things can happen. But this looks fine-tuned to me. You know, yes, you can believe it. Yeah, you can believe it. You can have this is what I call quantum Molinism, right? You can have a mind of God in which all the possibilities are stored. And then when we choose which measurement to make, the particles go outside space-time, look in this repository which outcomes to give, and then they read from this book. This book is a non-local identifier. If you want, this is the ontologization of Cohen-Specker contextuality, right? Cohen-Specker contextuality, non-local hidden variables when it comes to Bell tests. And then you really think these non-local hidden variables exist somewhere in a repository outside space-time. And then when you do a Bell experiment, you go and look that. There could be some form of finality, post-selection from the future, whatever, non-local forms, whatever that means, non-local, right? Local forms, Aristotelian, Thomist, it doesn't work, local doesn't work, okay? So the accident of space matters here, whatever, sorry, maybe it's a category, an accident, whatever that is. Okay, certainly I'm very positive to the fact that maybe serious metaphysics may solve that. Maybe it's just because we have a very materialistic particle-based metaphysics that we are surprised, and if you have a more correct metaphysics, you should not be surprised. Certainly, I think it should not be seen as a direct windows into the supernatural, right? Between metaphysics and supernatural is a gap, and I don't think that the violation of Bell inequality tells that a god or some angels are acting there. But some of my friends do, but whatever. And I think that's it, yeah. So if you want the technicality of non-locality, I've written a book. And although the first thing you see when you open the thing is the price, but actually, if you look more carefully, it's an open access. You can download the PDF without paying those pounds. And here is the QR code if you want. Okay. Thank you very much.
We have time for some questions for Valerio. Okay, yes, let's begin with.
Thank you very much. That was great and helpful in a lot of ways. I'm curious because you were emphasizing in particular the idea that when you talk about entangled, you're talking about states that are prepared as corresponding in the theory to be entangled, and particularly to get these measurements that requires very careful arrangement and preparation. But my understanding is, at least in theory, those mathematical correlations exist in lots of other states that we can't test very well. So there are mathematical descriptions of things in chemistry and chemistry
yes.
that exhibit these kinds of
Sure.
mathematical correlations. Do you? I mean, what does that mean? Does that mean anything to you? In the sense of does that mean that we should expect that there's
No. I fully
non-local things going on in chemistry and these sorts of phenomenon as well?
Okay, so let's see. Well, first of all, let's say in this moment, tentatively and non-Popperianly, I endorse quantum theory as a correct description of nature for the sake of all practical purposes. And therefore, I do agree that entanglement is everywhere, which, by the way, entanglement, if you go to quantum theory, entanglement is also the reason why I'm thermalizing with the environment. So this means that entanglement is really everywhere. I was emphasizing non-locality, but it's true that any model that would try to make sense of this thing should not, I mean, essentially should not depend, because of this, should not depend on space and space-time, right? It doesn't matter if I measure these things separately, not separated, the correlations are the same, right? So yeah, in that sense, I agree. And that's in the small paper on quantum Molinism by Antoine Suarez and myself, that's, and what I noticed there is that if you do that model in a trivial way, you end up in technical problems. So we fix a technical problem there. So you need to, your recipe should be fine-tuned again in a suitable way. But yeah, I do perfectly agree that there shouldn't be any difference. I mean, according to what quantum theory tells us, there shouldn't be any difference between entanglement between two things that fly apart and entanglement between the two electrons in the same orbital of a molecule, right? These are all described by entangled state. All that I wanted to say about that sentence is that I don't know if the word entangled refers to, I mean, it's all this correspondence between the theory and nature, right? I don't know, I mean, we can say that these things are entangled, but if you say, what does entanglement mean? I mean, to explain what entanglement means to a lay person, either you explain Bell inequalities, or you explain that, there is this vector space, as Paolo did, and then because you need vector space, you can sum them, and then you cannot split them again, right? But that's it. No, I fully agree that entanglement is entanglement, and it doesn't need to be tested I mean, it can be many-body physics, can be anything, yeah.
Okay, yes?
Thank you for the interesting talk. Just on the comment about conditional probability, I think we need to add an extra action. Take the Gödel theorem, which was pointed out yesterday. In physics, too, you have an incompleteness state. I think a simple axiom, which is one observation can give two pieces of information, either classically and or quantum mechanically. For example, flip a coin, probability heads up, I have. But in fact, if heads is up, I also know tails is down. And that runs right through all concepts of correlation, including quantum. So we'll clean up a lot of the nonsense about action as one observation, two pieces of information because of correlation.
Yeah, but I mean,
but then the type of correlation, quantum has the questions you're asking is an intriguing thing, but it does at least give us an answer whereby we can just handle the fact that there's two pieces of information. It's not a mystical thing of running communication fast as speed of light. It doesn't.
I don't think a mathematical description would tell me how nature does it.
No, I didn't say how it does it. That's it. But it's much more intriguing. I didn't say how it does it. At least we can cut down the discussion about fast and speed of light, less than speed of light. There's no communication. It's correlated at the beginning. They've separated right hand, left hand, although it's not deterministic. The correlates were non-deterministic.
You need to send some information from the measurement. Sorry, that's wrong. What you're doing is locally hidden variables.
No, it's you could but take this case of chemistry. If you're in an orbital, if something's in an orbital,
you create an entangled state. You create what the theory describes an entangled state, but the causal model you are doing is locally hidden variable. We can discuss the whole day, but it is.
Don't even look in parameters.
But the causal. We have a question down there.
Let's not do a local parameter.
Okay, next question. Yeah, let's go to Fernando, maybe. Yeah.
Yes, could you show the conclusions again, please? Yeah. Well, somewhere what you no, that's fine. The first one that you showed, yeah. When you say the windows into the supernatural.
Yes.
Yeah, but the thing is, it's true. I mean, you can never prove the existence of God scientifically. But the fact is that there are physical facts that very strongly suggest that there is something else beyond what can be materially controlled. And so that the closure of the physical world in particular, it's not supported by nature in the sense these experiments, I mean, you can take the view that the locality is a fundamental fact, and that kind of determinism is fundamental. It doesn't violate relativity because you cannot send useful information in the sense that you cannot introduce any paradox. So I think one thing is proving, another thing is strongly suggesting. Okay.
Well, let's see. Why is not dark matter supernatural? We don't know dark matter. We don't know what it is.
Because dark matter, we know there may be something that we don't see.
There may be something outside. There may be a fifth dimension of space-time that we don't perceive.
There are many proposals that are some of them very serious, like primordial black holes and so on. And
Here we have
there is room for a lot of physical interpretation, but here
we have Bohmian mechanics that if
Conformal relativity of Philip Adamson, I know him well, works in black.
yeah, okay,
There's no dark matter.
I have to bring order to the, okay.
Excuse me. Dark
Last,
is a
I mean, you say that you cannot within a materialistic picture, one can always invoke something else like a but another possibility is that it's just direct way for the spirit to participate. Of course, it's legitimate to look for other physical causes as long as one makes a testable prediction.
allow me to strongly disagree with the possibility that the spirit interacts directly with matter, but that's my probably materialistic upbringing. And
Then I only raise one question. Do you think that your free will is real or is an illusion? That's my. With this, I finish.
okay, my free will is a different.
Real or is an illusion? If it is real, there is something else. And this is the window, in my opinion.
Larry, do you wish to respond or?
No.
All right, so Father Matthew, can we have you come up to start preparing your talk? And maybe while he's doing that, we can take one more question. Maybe Ibrahim wants to say something?
So very, very nice talk. It's very interesting to see all of those, ways that it also leads to some loopholes. So, and loopholes justifications. So can you comment on the contextuality?
Mhm.
Because I mean, this is, in my opinion, is much more stronger argument than locality and, causality and other problems. Can you link it to the contextuality of quantum mechanics? Why the sequence of the measurement will give you different results?
Well, the two things are related and unrelated. There's a subtle relation between contextuality and non-locality, right? Because the contextuality in the usual sense, the context is a direct sum of things. Here, the context is a tensor product of things, so it's a little bit different. Here, the context is non-local, and in the other case would be, in standard single particle contextuality would be local. But I mean, I don't have much to say on contextuality. I mean, it's a very interesting observation, right? That you cannot define physical properties, all right? But at the same time, at the operational level, if you have a single particle, you always have a local variable model, right? It's just that the properties would have to behave in that particular way, that you have to take into account the whole measurement and not just that property. I mean, there are many things in quantum theory that need to be ironed out and explained. And for contextuality, I don't have any particular. For me, contextuality is essentially quantum mechanics. I mean, it's almost equivalent to quantum mechanics in the sense that it's a manifestation of. This one is device independent. I mean, this one, if you believe that there's no, that if you manage to assure that there's no communication, the falsification of local latent variable is device independent. The falsification of determinism depends on this assumption that I discussed, but it's device independent. So again, it doesn't matter if it's a photon, if it's a neutron, if it's not entangled, you don't violate. That's it. So that's
So I know there are more questions, but we have to move on. So let's thank Larry again.
Probably want to get the microphone.
And for you as well. Put this. Can you? Yeah, so go to your Wi-Fi, have an open access.
You have slides to show?
Yes. So you'll join the Zoom link. Zoom join.
All right, so while Father Matthew is connecting, let me introduce him. So yeah, go ahead and add your Zoom link. Father Matthew Raffray is a Catholic priest from the Institute of the Good Shepherd, where he served as the superior for Europe. He holds a master's degree in mathematics from the University Paris Jussot, a lyceum in theology from the Institut Catholique de Toulouse, and a PhD in medieval philosophy from Paris Sorbonne University, Paris. His doctoral dissertation, published by Verine in 2023 under the title Métaphysique des relations chez Albert Legrand et Thomas d'Aquin, reflects his longstanding interest in the metaphysical notion of relation. He's taught philosophy and theology at various institutes, most notably the Pontifical University of St. Thomas Aquinas, the Angelicum in Rome, where he taught ancient philosophy, epistemology, and metaphysics from 2015 to 2025.
Okay.
Myself speaks.
Time and space.
You have to mute your microphone and it speaks, right? His research interests focus on the relationship between science and faith, drawing on his background in both mathematics and philosophy. In the recent years, he's published several articles on artificial intelligence, examining its philosophical and physical implications from an Aristotelian Thomistic perspective. His current research explores the dialogue between contemporary physics and classical metaphysics. Alongside his academic work, Father Raffray is also actively involved in public outreach. Over the past several years, he has become one of the most widely followed Catholic priests in France on social media, with more than 200,000 followers on Instagram. We only had 200,000 followers each on Instagram, where he seeks to make philosophy, theology, and Catholic faith accessible to a broad. Yeah. All right. Now you can just show slides. So it's right there. Yes. Oh, yeah. Yeah. You have to share that screen. Window. Go to your Zoom. Go to your Zoom. Share. I remember that. Close. Timothy's 100. So bring up your, if you bring up your Zoom. So. Yeah, this is, it's one of those things that is not super common, but it pops up. Yeah. Like this is the second time I when I have to share the right thing. So this is the easier. So let me try.
So
I think it's very interesting to go on with this topic after the precedent talk, because I'm going to talk about Bell's inequalities, but under another point of view. So I'm going to talk not about theology or angels, neither about pure physics, but about metaphysics and a philosophical interpretation of Bell's inequality. So does quantum entanglement disqualify substance ontology? So from the most ordinary experience to the most sophisticated philosophical reflection, we are naturally inclined to think that things exist prior to the relations they enter into. Individuals appear to come first, relations seem to come second. This common sense intuition has largely accompanied, on one hand, the development of metaphysics in which substance is ontologically primary, while relation is an attribute inhering into the subject, added to the substance, and characterized by directing that substance toward another object external to it. This metaphysical position, characteristic of Aristotle and many of his successors, may be designated by the general term substantialism. Yet this intuitive conception of the priority of objects over their relations has also made possible in another domain the development of modern science. Indeed, to understand a physical phenomenon is to analyze it, that is, to decompose it into simpler elements until one reaches what may be regarded as its fundamental constituents. Gradually, however, this analytical method was transformed into a certain representation of reality, according to which what is primary is identified with indivisible elementary entities, atoms, in the original Greek sense of indivisible, possessing their own independent identity. Within this representation of reality, the relations between these elementary entities become secondary and derivative. The methodological ideal of analysis thus tends to become a metaphysical thesis, namely ontological atomism. The history of contemporary physics may, however, be read as a progressive questioning of this representation. Relativity first showed that physical objects cannot be conceived independently of the space-time structure within which they exist. Quantum mechanics then went even further. With the phenomenon of entanglement, the very possibility of completely describing the parts independently of the whole they constitute is called into question. The relations between elementary particles therefore appear to be more fundamental or ontologically prior to the elements themselves. It is precisely this difficulty that lies at the heart of Bell's theorem and of Alain Aspect's experiments, which confirmed it. For many authors, the results obtained, therefore, seem to impose a radical metaphysical conclusion. Relations must be acknowledged to be more fundamental than the entities themselves. Quantum entanglement would therefore require abandoning substance ontologies in favor of new relational ontologies, in which relations are prior to or constitutive of the substance they compose and determine. These metaphysical positions may be designated by the general term relationalism. Today, I wish to defend a different thesis. My purpose is not, of course, to challenge the results of quantum physics, but to examine the metaphysical interpretation that is often proposed on their basis. I shall argue that quantum entanglement does not refute the metaphysics of substance. Rather, it calls into question an atomistic conception of substance. More importantly, I shall argue that the transition from physical non-separability to a relational ontology rests upon a philosophical inference that is not necessary and that itself raises considerable difficulties. My aim, therefore, is not to return to the period before Bell, but rather to ask what remains of substance after Bell. First point, but I think we have already heard a lot about Bell theorem and its applications. So the end of local realism. In order to understand the metaphysical implications of quantum entanglement, it is first necessary to clarify what Bell's theorem and its experimental confirmations actually demonstrate. The philosophical conclusions often drawn from them indeed go beyond what the physical results themselves allow us to affirm. The starting point is the article published in 1935 by Einstein, Podolsky, and Rosen, the famous EPR problem. Their purpose was not to challenge the empirical successes of quantum mechanics, but to question its completeness. Einstein defended two principles. On the one hand, realism, according to which a physical system possesses objective properties independently of their observation. Measurement reveals those properties without producing them. On the other hand, separability, according to which two physically distinct and spatially separated systems must be capable of being described independently of one another. Entangled states appear precisely to contradict this intuition. The correlations observed between two distant particles no longer seem to be explicable by pre-existing local properties. Einstein therefore concluded that quantum mechanics is incomplete and should be supplemented by hidden variables capable of preserving both realism and locality. For nearly 30 years, this debate remained essentially philosophical. The situation changed in 1964 with John Bell. His decisive contribution was to transform this conceptual difficulty into a mathematically testable proposition. Bell showed that every theory satisfying both realism and locality, that is local realism, must satisfy certain statistical constraints, namely the Bell inequalities. Quantum mechanics, however, predicts in certain experimental configurations correlations that violate precisely these inequalities. The experiments carried out by Alan Aspect and his collaborators in the early 80s confirmed these predictions. Pair of photons prepared in an entangled state were subjected to measurement performed in experimental arrangements sufficiently far apart to exclude any ordinary influence between them. The observed correlations systematically violated Bell's inequalities. Subsequent experiments progressively reinforced this conclusion by eliminating the principal experimental objections that could have affected the significance of Aspect's results, particularly those concerning detector efficiency and the space-time separation of the measurements. These developments culminated in 1915 with the first so-called loophole-free experiments, which simultaneously closed the principal experimental loopholes that still remained open. Although disagreements concerning the interpretation of these results persist, as we have seen, their empirical validity is now widely acknowledged. Quantum correlations cannot be explained by any theory satisfying simultaneously the requirements of local realism. The philosophical significance of this result is considerable. For the first time, hypothesis concerning the very structure of reality became susceptible to experimental verification. Yet it is important to measure precisely what has been established. Bell demonstrates neither non-locality taken in isolation, nor the falsity of every form of realism, nor a fortiori the non-existence of substances or the ontological priority of relations. He shows only that quantum correlations are incompatible with a conception according to which physical systems possess intrinsic local properties that are completely determined prior to any measurement. In other words, Bell calls into question a certain conception of the physical independence of systems. One decisive question nevertheless remains. Does this crisis also entail a rejection of their ontological independence? It is precisely this inference that contemporary relational ontologies propose and which must now be examined. Second point, from physical non-separability to relational ontologies. The results of Bell's theorem soon extended beyond the foundations of quantum mechanics to give rise to a genuinely metaphysical debate. If entangled systems can no longer be described as collections of parts, each possessing its own complete and independent state, must one conclude that relations are more fundamental than the entities themselves? For a growing number of philosophers of science, the answer is affirmative. Entanglement would reveal that the relational structure of the world is more fundamental than the object it relates. The most influential formulation of this thesis is undoubtedly that of ontic structural realism, defended by James Ladyman and Don Ross. In Everything Must Go, in 2007, they argue that the results of contemporary physics require the abandonment of an ontology of objects in favor of an ontology of structures. Individual objects are no longer the primary elements of reality. Rather, they appear as nodes within more fundamental relational structures. These structures are therefore not relations between previously constituted objects. They constitute the primary ontological level from which objects themselves receive their identity. Michael Esfeld proposes a more nuanced position, which may be described as moderate structural realism. Unlike Ladyman and Ross, he does not entirely abandon individual objects. These continue to exist, but they no longer possess intrinsic properties sufficient to ground their identity independently of the relations in which they stand. As he writes, objects are individuated by the metrical relations in which they stand. Relations, therefore, do not replace objects. Rather, they become the principle of their individuation. The being of individuals thus appears to be essentially relational. This way of thinking is by no means an innovation peculiar to the contemporary philosophy of physics. As early as 1910, Ernst Cassirer argued in Substanzbegriff und Funktionsbegriff that the modern sciences progressively replace substantial categories inherited from classical metaphysics with functional relations. This shift, initiated long before quantum mechanics, seems to find in the phenomena of entanglement a particularly suggestive confirmation. The transformation from a metaphysics of substance to metaphysics of relation has also found developments independent of the philosophy of science. In Alfred North Whitehead's process philosophy, fundamental reality is no longer composed of enduring substances, but of actual occasions. That is, events whose identity results from the dynamic networks of their relations. The category of process thus replaces that of substance as the primary principle of intelligibility. This orientation finally receives an original theological formulation in the Trinitarian ontologies, developed in particular by Klaus Emmerle and John Zizioulas. Both take at their point of departure the Christian doctrine of the Trinity, understood as the revelation of a being whose unity is inseparable from the communion of the divine persons. For Emmerle, being itself is conceived as an event of reciprocal self-giving. Relation is no longer an accident of substance, but a fundamental mode according to which being communicates and realizes itself. Zizioulas radicalizes this intuition in Being as Communion by maintaining that the person does not first exist as an autonomous substance, which subsequently enters into relations. On the contrary, it receives its identity from communion itself. Relation thus becomes constitutive of personal being. A comparable emphasis on the primacy of relation may also be found from a different perspective in Martin Buber's philosophy of dialogue, where the I-thou relation is understood as more fundamental than the isolated individual. By the way, it is perhaps not accidental that these various forms of relational ontologies exhibit significant affinities with certain traditions of Eastern philosophy, particularly a special school of Buddhism in which dependent origination and relationality are regarded as more fundamental than enduring substances. A fundamental metaphysical difficulty nevertheless remains. Despite the differences, all relational ontologies tend to make relation the ultimate principle of the intelligibility of being. Yet a relation is, by its very nature, a being toward another, esse ad, in scholastic philosophy. It cannot be conceived independently of the terms that it relates. It can explain the manner in which beings are united, but not what constitutes them as beings, nor what grounds their own unity. To make relation the primary principle of ontology is therefore to attribute to an essentially relative category an explanatory function that exceeds its own nature. Ultimately, if everything is relation, it becomes difficult to account for precisely that which is in relation. Relational ontology admirably illuminates the structure of the reciprocal dependencies between beings. It is less successful in accounting for the very foundation of their being. This is why, far from rendering the notion of substance superfluous, it seems rather to presuppose it implicitly as the principle of unity of that which enters into relation. Third, the turning point, distinguishing formalism from ontology. We may now return to the central question of this lecture. If quantum entanglement so often leads to relationalist conclusions, it is because it is generally assumed that the structure described by the quantum formalism directly reflects the ontological structure of reality. It is precisely this assumption that must be examined. The question is no longer whether non-separability is real. The experimental results discussed above are sufficient to establish that. The question is rather what exactly the formalism of quantum mechanics describes and what one is entitled to infer from it concerning the structure of being. Since the work of von Neumann, the standard metaphysical framework of quantum mechanics has been that of Hilbert spaces. The state of a physical system is represented by a state vector belonging to a complex Hilbert space. More precisely, it is not the vector itself that represents the physical state, but its ray, that is its equivalent class under multiplication by a non-zero complex scalar. Observables are represented by self-adjoint operators acting on this space. Measurement probabilities are obtained by means of Born's rule, according to which the probability of obtaining a particular value is given by the square of the modulus of the inner product between the state vector and the subspace corresponding to the outcome under consideration. The entire predictive power of the theory therefore rests upon this mathematical structure: vector spaces, inner products, operators, probability amplitudes, and unitary evolution. In the case of a composite system, however, quantum mechanics does not simply assign to each subsystem its own state space. Rather, it constructs a new space known as the tensor product, which contains the set of all possible states of the composite system. This point is essential, for it is precisely at this level that the phenomenon of entanglement appears mathematically. When a system is said to be separable, its global state is completely determined by the states of each of its constituents. Knowledge of the part is then sufficient to determine the whole. There exist, however, states that cannot be decomposed in this way. These are called entangled states. The best known example is the singlet state, in which two particles possess a common state without it being possible to attribute to either of them a pure state of its own. The subsystems are described only by reduced states obtained from the global state. All the relevant physical information is therefore carried by the system as a whole. Non-separability is thus not a property added to the quantum formalism. It is inscribed directly in the structure of the tensor product and in the existence of non-factorizable states. Up to this point, however, we have described nothing more than a mathematical structure. It is here that the decisive philosophical point emerges. The quantum formalism describes state vectors, operators, probability amplitudes, and statistical correlations. It provides an extraordinarily effective method for predicting experimental results. Yet it contains no explicit theory of substance or of ontological dependence. It contains no theory of being. Nowhere in Hilbert space do we find a notion of substance, real relation, causality, grounding, or metaphysical dependence. The formalism describes the way in which certain physical quantities are correlated. It does not specify what the realities to which these correlations refer ultimately are. This observation may seem trivial, yet it is frequently overlooked in contemporary discussions. For one often passes directly from the mathematical structure of quantum states to conclusions concerning the ontological structure of reality itself. It is precisely this transition that I wish to examine. That entangled states are non-factorizable is a perfectly well-established mathematical property. That quantum correlations cannot be reduced to pre-existing local properties is a physical result that has been solidly confirmed. It does not follow, however, that relations are ontologically primary. Between those two propositions, there intervenes an additional step, a metaphysical interpretation of the formalism. This is what I shall call a category mistake, the confusion of a property of the mathematical formalism with an ontological property of the realities described. We are now in a position to formulate the distinction that, in my view, governs the entire debate. Physical non-separability concerns the structure of the states described by the mathematical formalism. Ontological independence, by contrast, concerns the mode of being of the realities themselves. These two questions are not identical, and indeed it is essential to distinguish them. For it is precisely on the basis of this distinction that it becomes possible to re-examine the notion of substance itself. Entanglement does not compel us to abandon substance, but rather to rethink what it means to be a substance. Rethinking substance after Bell. The results of Bell's theorem, therefore, do not refute the notion of substance. They refute a certain modern way of understanding it. The interpretation implicitly called into question is the one that identifies substance with an entity possessing a set of intrinsic properties that are entirely determined and independent of any physical context, namely local realism. Such a conception naturally accords with what we have described as a form of ontological atomism. Individuals are primary, their properties are entirely localized, and relations merely connect realities that are already constituted. It is precisely this representation that the phenomena of quantum entanglement render problematic. Bell does not show that substances do not exist. Rather, he shows that physical systems cannot always be described as collections of local determined and physically independent elements. What is called into question, therefore, is not substance itself, but its atomistic interpretation. This distinction makes it possible, I believe, to return to an Aristotelian Thomistic conception of substance. For Aristotle, substance is not first and foremost an isolated individual. It is that which possesses its own unity of being. The fundamental question is therefore not that of isolation, but that of unity. To be a substance is not to be closed in upon oneself. It is to be one. Thomas Aquinas deepens this intuition by describing substance as that which subsists in itself. Real relations, for their part, are always accidents, that is, beings which do not subsist by themselves, but always inhere into a substance, which thereby constitutes their principle of unity and communicates being to them. Relation is therefore neither a mere construction of the mind nor a primary principle. It always presupposes a subject of which it is a relation. Quantum entanglement thus appears in a new light. What is called into question is not substantial unity, but the modern idea that such unity must be reduced to the possession of locally distributed and independent physical properties. Nothing in Aristotelian Thomistic metaphysics requires such an identification. The distinction becomes even clearer if we consider the status of the quantum formalism itself. The state vector, the wave function, the operators, and the structure of Hilbert space describe the mathematical manner in which a physical system is represented. They make it possible to calculate the evolution of the system and the probabilities of experimental outcomes. And as we have seen, their predictive success is indisputable. Yet, this formalism does not answer the question of why these different physical determinations belong to one and the same thing, and belong to one and the same being. It describes a mathematical structure. It does not yet provide the ontological principle of its unity. It is precisely here that the Aristotelian Thomistic notion of substantial form becomes relevant. Substantial form is not an additional physical property intended to supplement quantum mechanics, nor is it a hidden variable. It belongs to an entirely different order of explanation. It designates the metaphysical principle by virtue of which a set of determinations constitutes one single being rather than a mere collection of properties or correlations. In other words, the state vector answers the question: how is the physical system represented and how does it evolve? Substantial form answers a question of a different order. Why are these physical determinations the determinations of one and the same being? The quantum formalism and substantial form should therefore not be opposed to one another, for they belong to two irreducible levels of the intelligibility of reality, two distinct orders of knowledge. The former describes the mathematical structure of phenomena. The latter seeks the principle of unity that grounds the very being of what is described. There is therefore no reason to identify the systems spoken of by quantum mechanics with the substances of Aristotelian metaphysics. The former belong to a physical theory, the latter to an ontological analysis. The two notions answer different questions and cannot be placed in competition without committing precisely the category mistake that we have identified. It thus becomes apparent that the debate opened by Bell's theorem concerns not only quantum mechanics, but also the very conditions governing the dialogue between physics and metaphysics. Bell's true lesson is therefore not the disappearance of substance, but the rejection of a certain atomistic conception of individuality inherited from modernity. By revealing that physical systems cannot always be understood as aggregates of independent local properties, quantum mechanics invites us to rethink substance, not as an isolated reality, but as a principle of unity, whose real relations express its richness without ever constituting its ultimate foundation. In this sense, far from rendering metaphysics of substance obsolete, the advances of contemporary physics instead reveal its necessity. The more physics refines the mathematical structures by means of which it describes reality, the more unavoidable becomes the question that those structures cannot answer by themselves. What is it that makes there be a being of which these are the mathematical structures? It is precisely this question that the metaphysics of substance seeks to answer. Quantum mechanics, therefore, does not announce the end of this metaphysics. Rather, it invites us to recover its deepest meaning. Thank you for your attention.
Thank you so much for the talk. We have time for questions. Yes.
Thank you very much, Father. That is magnificent. And it's the importance of philosophy. Metaphysics must be studied because there are two orders of knowledge and two different levels of abstraction. So you base it on reality, and then you go to a higher level of abstraction and ultimately to philosophy and metaphysics. So physics and metaphysics is just prior and foremost in understanding physics. We have to put philosophy and science together.
Okay, I think that was a comment.
Thank you for the talk. I wonder what, so you were your main point was to don't lose the concept of substance. I will try to, if you can clarify, when you have entangled particle, right? So I think you said clearly that the two particles do not lose their own identity, but nonetheless, the two identities are not enough to define the whole of the two entangled system. So how do we understand, you know, the substantial reality of the two independent particle, and nonetheless the fact that these two, you know, this is not enough to define the entanglement. So do we need to, so in the allomorphic picture, one we need to speak about substantial form and then accidental form that describe the entangled system? How would you describe that?
I would say that there is no physical way or mathematical way to answer this question.
Yes,
because the unity is artificial. I mean, the fact to isolate a photon or an electron or a physical being from another one is just a question of mathematical relations. So the unity between them is not a physical one, or the unity between them is something higher. So coming from the form and talking about the form, that's metaphysics. It's not supernatural. It's another level of consideration of being. It would be to take a very simple example. It would be to say, okay, my hand, I have two hands, and they act together. If someone just would look at one hand saying, okay, how can I explain the relation between this hand and the other one? I mean, the only explanation is the entire body. And so
maybe let me restate, is the two entangled system of the photon a full substance in itself?
No.
No, it's not, right? So you have two substances.
No. Okay, the entire system can be a substance.
So that's
but a photon is not a substance.
Okay, that's your
it's just a mathematical reality. So that's why we have such strange results, because they are mathematical realities, and to consider them as substances leads to major problems.
I guess we can discuss it.
Also the physical reality. In fact, the photon, that's like
Yes, because I think a very important point is, what is a mathematical formalism? Because mathematical formalism comes from reality. It's not something invented or something just in our minds. It comes from reality. So it means something. It means that it works. And so obviously there are some phenomena, some experimental confirmations of these inequalities. But I think we have to ask the good questions at the good level, and to ask for a relation between these two elements, entangled spaces, is not a good question, because the question of unity is not a mathematical one, it's a metaphysical one. So I think there is no answer on the mathematical or on the physical level.
The question is that a substantial unity of the two particles or not? I mean, anyway, we can discuss it.
So the two particles obviously are part of a common unity, but they are not substances by themselves.
One more question.
Spitzer.
Back. I think let's go to you, William.
So let's do some clarification, please. Could you say a little more about how substances are individuated on your view? Would you agree that substances aren't known through their causal powers, or are you proposing some entirely different way of knowing?
So the definition of a substance in the Aristotelian philosophy is to esti, so something, a something, and a something with its own unity is taken from the reality. So a substance is not a construction of the mind. It's not the fruit of the reasoning. A substance is something. For example, that's complex because there are different types of substances. But an animal is a substance. I can say this is such. This is a thing with a nature. And if we cut the animal in very, very different parts, there are no more substances. So a substance is linked to reality. And a substance is not just a piece of something. It's not just an individual. Individuality is important for a substance, but it's not enough.
So with that, I suggest we postpone the rest of the questions to the coffee break. Thanks, Father Matthew again.
What you're saying is that we have a honesty is that I think use better examination system. With physical smart.
Oh,
Go right ahead.
Areas is. Very
I like the monkeys.
No, you traveled a long way from here.
There's no chance you can feel it, right? So the fire of the idea is a creating those
Yeah, I'm trying to get these animals wrangled here, Father, or brother, I should say.
Whereas practice.
Test 1, 2, can you hear me? Test 1, 2, you can hear me better this way?
All right, we're going to begin again. Welcome back. So I'm happy to introduce the next speaker and Brother Guy Montalano, Society of Jesus, is the astronomer at the Vatican Observatory and the president of the Vatican Observatory Foundation. In 2015, he was appointed by Pope Francis to serve as the director of the observatory. Ended in 2025. He earned his SB and SM degrees in Earth and Planetary Sciences from MIT and his PhD in Planetary Sciences from the University of Arizona. An expert in meteorics.
Meteorites. Meteorites.
Thank you, Father. A meteorite position in Antarctica. He is also widely published in the field of faith and science. And he also published this little book here, A Jesuit's Guide to the Stars. And as a little personal tidbit, he appeared on the Colbert Report to advertise his book. And I hope you'll sign this for me after your talk, brother.
Right.
So I turn the time over to you.
Thank you. First of all, thanks for everybody for coming. I am not an expert in anything quantum. The one quantum course I took at the University of Chicago while I was doing philosophy as a Jesuit was basically, the guy said, everything in quantum can be explained with Lie algebra. He spent the entire semester teaching me Lie algebra and then derived all the equations, none of which had meaning that I had any understanding at all of. But he was right, yes. I also apologize. I've been in and out of this meeting because I've had other things calling on me. And in fact, I'm leaving immediately after my talk. There should be a lift waiting for me. I have a meeting with Archbishop Gomez this afternoon. So I apologize if I miss out on some of the talks, especially from friends of mine, or maybe enemies of mine. Yeah, depending on how the Jesuits and the Dominicans are doing.
Listening very closely.
If we learn from our mistakes, I'm hoping you will learn a lot today. I know a lot of us are in the faith science business and we run into people who want to use science to prove or disprove God. Especially, I think that runs into in quantum physics. There will be those who say, quantum physics proves free will, which doesn't really do that. Or as we'll talk about, another case where someone was going to use a result of quantum physics to what they thought would be a disproof of God. You can't do that because God is bigger than science. We've also encountered a lot of places where the science doesn't seem to make sense, and that can be very discouraging. So I want to give you the reasons that I believe in science
and in particular, the reasons why my faith, my Catholic faith, gives me the faith to believe in science. And how do I make this go to the next step?
She just advanced.
Ah, the arrow has to be there. Got it. All right, here we go. I'm going to give you an example of the best science of its day for 1500 years, which was Aristotle. You not only have all of the planets in their order, but you have the Earth at the center. Actually, the Earth is not at the center. The Earth is at the bottom. It's the dregs. The only thing closer to that center is the Inferno, which is, not where you'd want to say it was the most wonderful place in the world. But Aristotle, in particular, in describing the Earth, noted that the heaviest material, Earth, falls to the center, to its natural place, surrounded by water, surrounded by air, surrounded by fire. And this picture was common sense. Anybody who's dropped a rock into a lake or seen bubbles come up of the lake or seen a flame rise, okay, that's scary. What have we done?
I didn't do it.
All right, I'll wave my hands because frankly, the pictures are there mostly to give me a sense of, there we go. Can we do this again? That didn't do anything. I have to have my, there. I'm not used to these Windows machines. This gave rise to an interesting problem. We know from looking at red sunsets that the fire is completely encasing the Earth. We know from breathing air that air is completely encasing the Earth. Why isn't there water completely covering the Earth? It seems to be a very logical place. Why do we have dry land? Well, there were people in the Middle Ages who cleverly misused scripture by quoting this part of Genesis, Genesis being a totally different systematic cosmology than the cosmology of Aristotle. But what the heck? There's this passage here, we can use it. God said, let the waters that are under the heaven be gathered together in one place and let dry land appear. Well, you start with this picture of the Earth surrounded by water, and you have God magically pulling all the water to one side, leaving a spot of dry land. That's dry land is still the center of the universe. It's the water, but of course, parts of the water are going to be farther from the bottom of the universe. And that means if you went sailing on those waters, you're sailing uphill. That's why they're called the high seas. And you will never, ever encounter any land until you reach the other side. That's why Columbus was so convinced that he was reaching India when he next reached dry land. Not only that, you can prove experimentally that this must be true. Go to the beach on a very still day with a tube that you have perfectly leveled and point it towards the horizon. And when you do that, you will actually not see sky, you will see water. Because the refraction of the air actually makes the horizon look a little bit above. They didn't know that then. They didn't know about, they made a prediction, the experiment proved the prediction, therefore the Earth must have water pulled to one side. Not only was this consistent with what they experienced, it was a proof of the existence of God. This is from 1777. You'd think they would know by now. Well, among the arguments to prove there is a God, number 4, the being of the vast sea, where there's such an abundance of waters, some think higher than the earth, where they're still bounded and restrained from overflowing and drowning the land and its inhabitants, as once happened, as we all know. This is clearly nonsense. But it's not nonsense. It's common sense. There actually are planets that are completely covered with water, and then air, and then plasma, Uranus and Neptune. Just doesn't happen to be our planet. There are icy moons that are completely covered with water, just don't happen to have any air. The first mistake was assuming a logical leap that since there's so much air, there must be so much water, when in fact, it doesn't have to be that much water. There can be just a thin layer of water, which is actually what we have on Earth. The second assumption was misapplying a principle of a completely different cosmology because it was fun to use this. There's a different mistaken conclusion you can make from this. I taught at a wonderful Jesuit school, Loyola College, now Loyola University in Baltimore. And I was doing Astronomy 101, you know, moons for goons. And one of my students, I assigned, because none of them knew enough mathematics to do homework sets, I gave them essay questions for a midterm. One of them came back not answering any of the essays I'd assigned, but a long treatise on how Thomas Kuhn says that science is only what you think it is, which is not what Thomas Kuhn says. And furthermore, if we used to think science said this, what makes us think that science is saying anything better now? Why should I even study this stuff? Because you're going to change it all in 20 years anyway. And in a sense, he has a good point. Why do we have confidence that even when we make mistakes, we're gaining more knowledge? Where does our confidence of doing science come from? Gave another talk at a very odd place, Oral Roberts University. I'm thinking, I'm a Jesuit, what are they doing inviting? Turns out they're really nice people. And the faculty and the president of the university were very welcoming. But I spoke in a classroom and one of the students looked at me and says, "Do you take scripture seriously?" And the answer is yes, because scripture is what gives me the courage to do science. Here's Genesis 1, the picture of the earth, the flat earth with a dome and water above and below. And we know this picture. This is pre-Aristotelian. Does the Bible saying this mean I have to believe the Bible? No, this is the best science of the day when Genesis was written. When was it written? It was written during the Babylonian captivity. This is Babylonian cosmology. The Babylonians had this creation story where the gods were fighting among themselves and a dragon came along named Tiamat. The name is preserved in the word for chaos in scripture. One of the reasons we can identify it as, a Babylonian origin. And the gods are busy fighting themselves. The dragon is killed. The dome of the dragon's body is what we are inside of. That's what you see outdoors when you see the sky coming down. I guess he had a blue stomach, but we're inside. By accidents, human beings were made in all of these struggles. But the human beings all got together and created the ultimate pinnacle of human achievement, the city of Babylon. And the Jewish scholars had been dragged off from Jerusalem, working for the government of Babylon, didn't like their kids hearing this, because this is not what they believed in. So they took the creation story and changed it. And it's the changes that are important. It's the changes that hold true to this day. First of all, the story begins, in the beginning, God. God is outside of the universe. God is there before there is a universe. That's what supernatural means, not, Casper the Friendly Ghost. If there were a Casper the Friendly Ghost, that would just be another part of science alongside quantum that we don't understand. By having God outside the universe, this goes back to what Giuseppe was saying yesterday morning, Wittgenstein, a purpose for the universe cannot be found in the universe itself, but only outside the universe. The chair you're sitting in only has purpose because there's something not chair sitting in it. Only a supernatural God can give the universe meaning, but it does give the universe meaning. Also, God is one. In the beginning, God. God creates in a way that is as logical as day follows night. These are the 7 days of creation in a cathedral in Cairns, starting with modern physics and Hubble images. It's a fabulous cathedral if you ever get there. God creates logically, and God creates willfully by speaking words. It's deliberate. It's not by accident. We use the word logos as, the origin of logic. Remember, it's also the origin of word. There are no nature gods. So if there are no nature gods throwing lightning bolts through it, then we are free to ask, what is the logical way to explain lightning bolts? I mean, the model of nature gods is perfect. It explains everything. It explains everything perfectly. It doesn't have any predictive power. Just as the Ptolemaic system of planetary orbits, if you have enough epicycles within epicycles within epicycles, eventually you can match any orbit. It's called Fourier's theorem. There's a guy, you can go up on the internet and type in Fourier Homer Simpson, and he has traced out a picture of Homer Simpson using Fourier cycles and epicycles. It's fabulous. But it has no predictive power. It doesn't teach you anything new, unlike Kepler's laws. The first words are, let there be light. Creation occurs in the light. Nothing is hidden. God is giving us a universe that makes sense and giving us the power to think about how it makes sense. And also a universe that is good. If you believe that the universe is fundamentally evil, chocolate was invented to make you fat and give you acne, and we should meditate to a higher stage. No. According to scripture, according to Genesis, chocolate was a creation of God to give us a foretaste of the goodness of heaven. It should be treated like a sacramental. Not a sacrament, but a sacrament. Finally, what is the ultimate stage of creation? What is the last and most wonderful thing created in the Genesis story? Not the city of Babylon. Man is on the sixth day. The ultimate creation is the weekend, the seventh day, the day of rest, the Sabbath. And this is important because it says that we were created not just to feed ourselves, but to appreciate the physical world and the creator who made it. We were not only given the power to understand the universe, this is our ultimate goal. This is why we were created, to be scientists or artists or musicians, however we express ourselves in ways that don't directly put food in your stomach. When I was a postdoc at MIT, I had this, I was turning 30. I'm thinking, oh my God, I'm getting old. I'm wasting my life. I'm worried about writing papers on the moons of Jupiter that only 5 people are going to be interested in, and 2 of them are my enemies. Why am I doing this? And that's why I quit being a postdoc and joined the Peace Corps. I was going to do something good for people. They send me to Africa, and within a few months, I'm teaching astrophysics to grad students at the University of Arizona, or University of Nairobi, rather. Why am I doing this? I went up country every weekend to visit my other Peace Corps volunteers, and I had a little telescope, and everybody in the village wanted to look through the telescope. And they'd see the rings of Saturn. How many people here have ever seen the rings of Saturn in a little telescope? How many of you have ever done that and not gone, oh, wow? And they went, oh, wow. And then they wanted to know, what is that? How does that relate to who I am? How do I fit in this universe? The big questions. The question, I had a cat in those days, which was very clever, better at being a cat than I could be a cat. But my cat never wanted to look through the telescope. Feeding your soul is what makes us human. Feeding your soul is what we're commanded to do on the 7th day. That's why I do science. Now, you could argue, do you really need to know that the world is round? Do we really, the guy, whoever wrote Genesis, didn't know the world was round and was probably a pretty good guy, male or female. We don't know who wrote it. Do you really need to know? Most of our lives we spend not even realizing that the world is round because it doesn't matter. There are, saints long before there was quantum theory. Do we really need to know quantum theory? After all, the most important thing is to be a saint, right? This is kind of the attitude that we find in another piece of scripture. The dialogue between Job and God. In chapter 9, God comes speaking to Job, and Job's going, oh, yeah, right. I mean, okay, you're right. How can a mortal be just before God? If you wish to contend with him, you couldn't answer him once in 1,000. You built the mountains. The mountains don't even know it. You can overturn them in your anger. You shake the earth, and you command the sun, and it doesn't rise. You seal up the stars. Who else but you stretched out the heavens and made the Bear and Orion and the Pleiades? All of this is beyond understanding. I'm just a little guy. You're right. I should shut up. God doesn't like that answer. In chapter 38, he replies, where were you, who darkens the world by the words without knowledge? Where were you when I laid the foundations of the earth? Who determined its measurements? Who stretched the line on it? On what were its bases sunk? Do you know the way to the dwelling of light? Asking us to do photon experiments, I guess. He's saying this not to emphasize I'm so much smarter than you, but to invite Job, if you really want to know me, come and discover the dwelling of light. Come and discover who I am. One other piece of scripture that I take very seriously. The story in 2 Maccabees, you may know the story. The king is ordering all the Jews to either eat the meat that's been dedicated to the nasty god, or else you're going to get killed. There's a mom with 7 sons. And one after another, they're sent off. We never even told the mom's name. But when her youngest is about to go off and be killed, she says, look to the heaven and the earth and see everything that is in them, and recognize that God did not make them out of things that existed already. Which, of course, makes you think of Leibniz. Why is there something instead of nothing? The nothing that this is talking about is not merely a vacuum. When Aquinas says creation is from nothing, the nothing he means is not even space and time. The God who was there before space and time were actually created. Now, my second picture up here is a picture of, next to Leibniz, is a picture of Georges Lemaitre and Albert Einstein. Most of you recognize who Lemaitre was, I'm sure, the priest who came up with the Big Bang Theory. I'll point out he was not a Jesuit. He hated being called a Jesuit. It is possible to be smart and not be a Jesuit. And then Hawking, who we'll get back to in a bit, because the genesis of our modern cosmology in many ways comes out of the discovery of Einstein's general relativity and its confirmation in 1919 by observing during an eclipse the position of a star right next to the eclipsed sun and realizing that the sun's gravity had bent the light in such a way that this confirmed Einstein's predictions and not Newton's predictions. I have up here also a bit of the headline from the 10th of November, 1919 in the New York Times. Lights all askew in the heavens, men of science, more or less, agog over the results of the eclipse observations. Einstein theory triumphs. Stars not where they seemed or were calculated to be, but no one need worry. A book for 12 wise men, no more in all the world could comprehend it, said Einstein when his daring publishers accepted it. Probably as kids, you heard a lot about relativity and how incredibly, only 12 men could, all of these myths were invented in this headline. in the New York Times, because when the press release, the press conference was held, Eddington was announcing his results. The only reporter that the New York Times had in London free that day was a guy who had been sent there to cover a sporting event, a golf tournament. And he treated astronomy as if it was, a sports event. And this is the Babe Ruth of sports. The Babe Ruth the Babe Ruth of science. And that's why you've got to have, crazy wild hair and a German accent to be able, because that established our idea of what it meant to be smart. The idea, as we all know, is that mass warps space and time, and gravity is a warping of space and time. And Lemaitre's idea, he's pictured here next to his postdoc advisor, Eddington. Lemaitre's idea was that there is a problem, as many people realized, if mass is warping space and time and you've got all the time in the world, the gravity will eventually cause all of the mass to collapse into one place and the entire universe will envelop inside itself and then we shouldn't have a universe anymore. Eddington says, well, I've also heard about this quantum idea of states of exceedingly high energy. What if you actually started with a point of exceedingly high energy and allowed it to expand from that cosmic seed? Among other things, you could explain the motions of the galaxies that have been known for 20 years. And I predict that if you could measure the velocities of the galaxy clusters as a function of distance, the ones further away would appear to be moving faster in such a way that all of them would have been at one place at one time. We know the history of the rest of this, the idea that, oh my gosh, this means the universe has a beginning. Hawking and his co-author Leonard Latimer write a book around 2012 that turned this on its head. Hawking has decided a priori that can't be a God. Therefore, how do I get around where did this beginning point come from? And he says, well, if you start with the space-time continuum, there will be quantum fluctuations. Hence, quantum theory is my rescue. I can wait long enough, I got all the time in the universe, until one fluctuation is big enough that it actually triggers off the Big Bang. In this way, the universe creates itself. In this way, I don't need God to, as he puts it, light off the blue touch paper to start the fuse to get the universe going. Now, the philosophers in this room can see a few of the problems, like where did the space-time continuum come from? And the quantum fluctuations and the laws of that, where do they come from? Worse than that, he is confusing the Big Bang with the creation from nothing. The Big Bang is what happens after creation has occurred. Not only that, he is confusing God with the thing that started the Big Bang. And this goes back again to another point that Giuseppe made Sunday night. To believe there is no God, you have to have a really clear idea of the God it is you don't believe in. Otherwise, how can you be sure there isn't any God? And most of the gods that my atheist friends don't believe in, I don't believe in either. And I rather they were atheists than people who believed in a God that I think is false. They're one step closer, because I only believe in one more God than they do. We're not that far apart. On the other hand, he's saying, Hawking says, because there is a thing called gravity, the fluctuation of space-time, I don't need God. He's saying that whatever started the universe, I'll call God. And then he says that gravity is what started the universe, which logically says to me that he thinks that gravity is God. Maybe that's why he thinks Catholics celebrate Mass. The real interesting philosophical point to take from this is that our science will continue to change Every new step in science is going to seem weird and unimaginable and difficult to accept. We're all happy with Newtonian physics here. Have you tried teaching freshmen physics? When they're coming in, they're not at all happy with Newtonian physics. What is space? Don't ask. What is time? Don't ask. I'm reminded of this wonderful cartoon. It's two fish in a fishbowl looking at a snow globe and saying, great, now I'm going to have to come up with a whole new cosmology. In some ways, we're the fish in the fishbowl, not realizing that there's a table or some folks, taking a laugh at us. And yet, what's fascinating is how the principles of our religion and many ancient religions hold true and are foundations on which we can base the science we do, to give us the confidence that the science we do is worth doing. Again, in the previous talk, Gödel came up. The idea that every logical system has to begin with axioms makes you then ask, what are the axioms of science? We have to believe there is a real universe, otherwise what the heck are we studying? There are some quantum people who don't believe that, but we'll put that to the side. You have to believe that it actually follows laws. And one of the great things of quantum theory is even when you invoke chaos, well, even when you invoke randomness, which as we heard, you really can't define, nonetheless, it can predict with great precision the probability of things happening. But the third thing and the most important thing, and the thing that Stanley Yaki pointed out years ago, is particularly true of the religions of the book. You have to believe that studying the universe just because it exists, just because it's interesting, just because it gives you joy, is something that grown human beings should be free to do. It's not going to make you rich. It's not going to make you famous. Not going to get you girls. Didn't work for me. Why do we do it? Why are we sitting here for 3 days asking these questions? Because ultimately, we experience joy in understanding, and that joy is always an indication of the presence of God. Thank you very much.
Thank you for such an inspiring talk. Questions from the group?
Or comments? Yeah.
Do you think we need an explanation or an interpretation of the parts of the universe that we think we'll never be able to understand? Is that some joke of God's or a way to humble us a little bit?
I think rather we have to recognize what do we mean by we, though parts of the universe I will never understand. But I'm hoping that as human beings, we don't end ourselves in the next 10 years. And we have a chance so that 1,000 or 1,500 years from now, they will look with admiration and a little bit of condescension at our understanding of quantum physics today. Because part of this faith is the faith that all of it ultimately is understandable. I'll give you an example. There was a philosopher, French philosopher, Comte, who in the 1830s described material that we knew there must be knowledge what we'll never have. We will never be able to go to a star, collect a sample, bring it back into the lab and find out what stars are made out of. And 20 years later, we're taking spectra of stars and working out their chemical composition. He was convinced this was knowledge we could never have. And within his lifetime, it was knowledge we did have. So I don't think we should ever give up the quest, but we should also never think that we've got it done. The hardest thing to be a person of faith or a person of science is to start by saying, I don't know. Because if you think you know, then you're dead. You're dead in the water. But the relation that we have with science, or the relationship we have with God, ultimately is a relationship of love. And if you think you know your friend or your spouse or your kids, and you got that figured out and there's nothing more to learn, then that relationship is dead. But if you're, I mean, my parents lived to be for 72 years in marriage. They made it to 197, 97 and 100. And they were still learning new things about each other. We'll still always have new things to learn about the universe and about God, which is why I'll be asking for money for do more work next year.
Another question or comment? Yes, Fernando.
My question is a bit out of the box, but
Sure.
at this level, I think it is relevant. How would you compare science and art?
Science is a form of art. Astronomy is not the study of stars and planets. It's the study of what human beings have thought about stars and planets, and the marvelous creations that we have come up with in imitating our Creator to explain what we think we're seeing. And the old explanations, we can appreciate their beauty even when we see that they are no longer adequate. I'm reminded of C.S. Lewis's book, The Discarded Image, where he goes on at great length of the medieval view of the universe that we started with, and says, you know, a lot of you probably want to remind me that it had one flaw. It's not true, but it was beautiful. And I can appreciate that beauty, even as I can also appreciate the lovely things that make me realize it's not that it's a lie, but rather that it's woefully inadequate. In the back there, yeah.
Oh, yeah, in the far back.
Hi, brother. I'm Sonia. I teach young physicists of 13 to 18 physics class. I have your poster in my classroom on a wall of Catholic scientists with the mirror so they could see themselves as the next Catholic scientist. So they're going to love hearing from you. And I just want to know what advice or any words for these young people that are interested in physics, but also believe in God. They have a beautiful faith, and and just any advice that you would have.
Two things that I would say. Again, the first echoing point 3 of Giuseppe's talk on Sunday. I mean, why are we meeting? He had actually so much good stuff that first day. You just take that and walk away with it. A great way to reach people at the beginning is through the history of science. Tell the stories of the people. The Galileo story, actually, you know, it was not an anti-church and science thing like that. The church still screwed up, but not the way that people would want you to believe. The story of Maxwell, we heard, of Ampere and Volta. Have them look up their stories in Wikipedia and see how Catholic faith has inspired them to do the science. See it in the stories. And you can find a lot of that in the Catholic Science, the Society of Catholic Scientists website, or our own website, click there. And so we've got a lot of that material available. The other thing, anybody who's teaching high school kids, I look at myself as a scientist, you guys who are scientists. What did we learn at high school that we use all the time? Writing, art. I learned how to analyze data by analyzing poetry. You look at a poem and you say, what's the one word that doesn't work? Why did the poet do that? There's the key there. This is the data point that doesn't fit the pattern. Either he was a lousy poet or he's using us to try to tell us something. Because all the work we do as scientists, ultimately goes back to the question of art. It's communicating with other people, learning how to listen to that conversation, learning how to contribute to it. And they ain't got to teach you that at MIT. You've got to be able to know and understand language and to be able to write and to be able to create images. You learn to do that in high school.
Yes.
Do you ever think we'll figure out what's that life principle? What makes aggregated molecules live? Do you think we'll ever?
About 10 years ago, the University of Arizona has this great program, 7 lectures in a row from 7 scholars at the university on whatever particular topic they chose that year. And they fill the biggest auditorium at Arizona. It's a great program. They asked me to give the opening one on life. A topic again, which I really haven't done any work on, but it made me dig into what do you mean by life? And we realize that as scientists, we have much too narrow a concept of what a definition is. We want to find the boundary. We want to find the instrument that I can put on the lander on Mars that says, yes, there is life, no, there isn't. When in fact, you know, the Chaim to the song to life in Fiddler on the Roof. I was in Fiddler on the Roof, by the way. I played the rabbi. This is at MIT. The sense of what is the core of life, what makes it exciting and interesting, is different from just saying, well, it's a local reversal of entropy. Many of the definitions we have of life in terms of chemistry, you can apply to plagioclase. But you know, they haven't had a 7-part series at the university on the nature of plagioclase yet. What is it about life that makes it interesting to us? We have to, I think, ask questions like that in a bigger context and let science inform that context, but not control it.
All right, let's thank Brother Guy. So you can prepare? Maybe I can, that would be lovely. Andrew Jordan. Great. Get this out of your way. Screen share, yeah. So the Zoom link is there if you don't already have it. You already set. You're doing great. All right. You're so efficient. You've done this before. All right, I'm happy to introduce our next speaker. So it's Professor Joseph Yost. He did his PhD from the University of California, Berkeley, and is an elected fellow of the American Association for the Advancement of Science. He's also the Senior Vice Provost for Research at the Catholic University of America in Washington, D.C., a position he started in 2020. He's done a lot of great things there. He's elevated the university's #1 Carnegie Research status, and he's an expert in developmental biology, and he spent a lot of time at the University of Utah. Without further ado, I'll send the titles on the screen. So thank you so much.
Very good, thank you. So when Vincenzo asked me to give this talk, I reminded him I'm not a philosopher, I'm not a theologian, and I don't know anything about philosophy. He did not tell me I was falling for the guy. So I want to talk today. So what we talked about is this was before the recent letter from Pope Leo came out, and so I was anticipating that we're very excited about that. We do a lot of work in the artificial intelligence area. And so I thought, well, let's use that as a springboard to talk about the outcoming encyclical as well as some of the previous responses to emerging technologies and emerging technological revolutions. And so as a scientist, I will probably describe to you more failed experiments than successful experiments. And so the experiment of trying to put together a timeline of technological innovations and a timeline of the encyclicals that have come out since Leo the 13th was quite prolific to Leo the 14th. It was a slightly failed experiment, but we'll walk through part of it. And then I want to use this middle part of my talk to sneak in some biology, because I have a PhD in genetics and I work in developmental biology. And then I want to finish with what we're doing at the university as an outward-facing approach to really start tackling the Catholic responses to the multiple emerging technologies that are coming out right now. Very good. So this slide here, it shows us Leo the 13th. This is actually a statue in our lobby in the building that my office is in. So I walk past him every day. He looks at us and waves his hand at us, and occasionally there's a little cardinal on his fingertips, because that's our motto at the Catholic University. He founded the Catholic University of America. So we're very excited when our new Holy Father came out and chose the name Leo, really much in response to Leo the 13th. So we now have two Leos. We're flanked by Leos at the Catholic University. Leo the 13th, as I mentioned, was very active, very outward looking. In 1879, he published an encyclical, Eterna Patris, which really amplified St. Thomas Aquinas and the scholastic approach. And really the importance in that encyclical, he goes through very strongly the point about discussing faith and reason and how those two aspects of humanity are importantly interact. In 1879, elevated now St. John Henry Newman as cardinal, which is a very radical thing to do. Newman was not a bishop before he became a cardinal. And it was really kind of reaching out and saying, this guy, Sir John Henry Newman, is a really important thing about how we do Catholic education. He founded the Catholic University of America, as I mentioned, and then Leo the 14th, one of his acts recently was to declare Newman as one of the doctors. So we're flanked by the two. No, sorry, there's two Leos. So there's many revolutions, and people, as the AI stuff comes out and as reading the encyclical comes out, people talk about it's a response to the new, quote, new industrial revolution. So I took that and said, let's go back historically and track out what the various industrial revolutions are. And as is true in much history, the boundaries are fuzzy in historical aspects. The World Economic Forum, if you can trust these guys who gather in Switzerland once in a while, calls out 4 industrial revolutions that are listed here. And they're obvious ones: steam and water and energy, lessening our mechanical work as humans, the division of labor and electricity in the 1870s, the railroads, that sort of thing. 1969, the big electronics, transistors and computers and all the information technologies coming out. They then called out a question mark, this is in 2016, of cyber physical systems, really kind of artificial intelligence interacting with computational systems. And they just came back again with another thing talking about human-machine collaborative framework. Now, how that timeline plays with the Catholic response has always been to remind us of human dignity, the importance and the centrality of human dignity. And I gathered here during this week the various quantum revolutions, and y'all have opinions on these things. There's quantum 1, we heard a lot about, quantum 2 from the 60s, Bell, et cetera, onward. And then this kind of debate, well, maybe there's quantum 3 going, and maybe that's another new revolution in this field. There's also revolutions, technological and scientific revolutions and biological timelines that I'll mention briefly. So I abandoned that experiment because Pope Leo the 14th did it for us in his new encyclical. He laid out beautifully. It's a really beautiful document. And then listed here on the right-hand side of the slide is about 15 or more different encyclicals that he laid out and he called out to remind us that the things that he is putting forward are not new things in some sense, but they are new things because they're a re-explanation of Catholic foundational intellectual thought and really how the Catholic social teaching, if you will, that really started with Leo the 13th and has moved through all of the popes from there to our current pope. So I'm not going to try to align this long list with the various technological revolutions that have happened across the world, but I want to use that opportunity as a springboard because we haven't talked about the encyclical here this week to really lay out the 5 principles that Leo the 14th illuminates and calls back to the other encyclicals on. The first and very strong one. See, these are things that those of us who are all familiar with Catholic social teaching will say, yeah, of course, these are the things that we should be doing. The first is the common good. And one that really attracted my attention was that it's an illusion to think that purely, simply pursuing one's own progress without caring for others is sufficient to contributing to the good of all. And so we often think that we're doing good stuff here and it's going to reflect on the society, but we The second is the universal destination of goods. And that funnels through several encyclicals in the past. And the idea that there's resources on the earth that all humanity, that should be available to all humanity as part of God's creation. We typically traditionally think of that, okay, water, air, we all need air and those other things that human beings need to live. But here he lays it out that in the context of the Wealth of Nations quote, depends increasingly on knowledge and on technology. And when these goods remain concentrated in the hands of few, without adequate forms of sharing and access, a new imbalance is creating that contradicts the universal destination. And this is important to think about as we think about large databases and large access to databases that really impact people's lives. The third and fourth, of course, are the classic subsidiarity and solidarity. And what caught my eye in the subsidiarity point is that he reminds us that from the time of Leo XIII through St. John Paul II, that the concern was focused on the state. Subsidiarity, of course, is the principle that individuals and families, the local communities, are the place where decisions are being made, not a top-down approach to us governing our lives, but a bottom-up approach with our families and our individuals. And here, what was interesting to me was that Leo XIV called out that in the past, those concerns were about the state imposing issues and that sort of thing. And really, here he says, well, we have to be concerned about other impositions and aberrances against subsidiarity that's focused largely in large public or privately held corporations. So sort of a new view of how we need to think about these states. In solidarity, he reminds us what solidarity is quite beautifully, and then his final, the fifth, is of social justice, and the idea that social justice helps us to recognize, quote, that injustices do not arise solely from wrong choices of individuals, but also from structures, mechanisms, and economic and cultural systems that produce inequality almost automatically. And as people think of in society about artificial intelligence and the other emerging technologies, this is an area that people are very concerned about. Other things that are becoming in happening lives. He starts and trickles through the whole thing, and we've already alluded to it here. The idea of rebuilding the walls of Jerusalem, and he points out that the way that was done was that Nehemiah started with praying. He was faced with this issue that his beloved Jerusalem was changed, just like people are concerned our society is changed. And he started with prayer, and then he started working with his fellow people, with the families and the individuals. And each family and each individual took on a section of the wall or a gate and assigned themselves to rebuild that section of that wall or gate. So it's very much bringing in those five principles in that story of Nineveh, of rebuilding Jerusalem. And he alludes, Leo XIV now alludes to men and women being prepared to enter the construction site of history. So the things that we're doing on the technological edges are the new construction site of history. We don't want to be doing it alone like the Tower of Babel. We want to be doing it as groups, as communities, and as examples, for example, this week of people really talking about how these things. And he calls everybody out to do that. Get to work. Laboratories, tech, schools, media, institutions, and says, let us not be afraid to get our hands dirty on the construction site. So we're really called to lean into it. We're very proactive. As a biologist, I was a little bit disappointed. I mean, it's a very full document, but there wasn't much biological anthropology document. That's okay. The same was true for Antigua et Nova that talked about during Francis's time that talked about the artificial intelligence revolution. But I remind myself that the Vatican documents are very thick with focus on human biology, human anthropology, including Dona Vita, Evangelium Vitae, of course, spectacular document, and then things from both Pope Benedict reminding us of the dignity of persons, Laudate Se from Francis, really focused on human dignity and the importance of dignity. So the biological revolution, just like the other revolutions we talked about, you can't get three biologists in the room and have them agree on what are those key points of what happened historically for biological revolutions. There's a complex slide that just says there's a lot of stuff that's happening, new transformations of understanding of biological and biomedical aspects. There's applications across those domains, but there's also very serious ethical risks to all of those domains that we have to manage. And just calling some of these things out that are current topics of emerging technologies, in vitro fertilization, human cloning, iPS stem cells, they're a good thing. CRISPR genomic engineering, which can be a good thing or a bad thing, depending on how it's applied. Embryoid bodies that I want to raise a flag to people to think about. This is a new emerging technology that very significant ethical concerns. And artificial intelligence and other information systems overlaying those things are really making for a challenging time. So my second part of the talk, I want to talk about symmetry and symmetry breaking, or asymmetry. So the physicists are going, yeah, we talk about symmetry all the time. We talk about asymmetry, but I'm going to sneak in biology instead of physics. So symmetry and symmetry breaking really is an essential part of how the biological system is put together. You often start out with symmetries, but they're very unstable, and they have to break in order to form the human form or the species form or the animal form. There's a very important breaking of symmetry to asymmetry throughout the development of organisms. And I want to spend a couple of minutes just giving you a view of what that is. And the simple example here is, think of it as a globe, where it's got, median longitudes and latitudes. When it's symmetrical, there is no difference in any of the longitudes. But upon fertilization, if that cell is a single cell egg, upon fertilization, the symmetry break to take that symmetrical globe cell and turn it into a very important asymmetry. And that very important asymmetry is what gets the whole internal engine started when that single cell zygote becomes a full organism, whether it's a fish or a frog. So that initial breaking of symmetry is something that my group and many others have studied over the years to understand how that process works. And so a snapshot of the biology of symmetry breaking. So organismal forms and their functions are built through mechanisms that are not optimized. If you look at how biology works, it's messy, it's sloppy, it's warm, it's weird. It's not, if I were an engineer or a physicist or computer scientist, the way biology is built is not the way I, as one of those disciplines, have built it. It's really unusual, and there's a really lot of interesting things happening in it that seem very inefficient. And it's much beyond emergent properties. And a quote from Schrodinger, who wrote the book that was mentioned earlier, What is Life, quote, living matter, while not eluding the laws of physics as established to date, is likely to involve other laws of physics, hitherto unknown, which, however, once they have been revealed, will form just as integral a part of science as the former. So there's a lot to unpack in that quote, but it really reminds us that there are emergent properties in biology that get well beyond what we know about in physics and chemistry and other aspects of the hard sciences. And so, a brief history of biological symmetry and asymmetry. So if you think about biological forms, pick any organism, and it has symmetry and it has asymmetry. And so the drawings here with the famous Leonardo da Vinci in the middle with the human form. There's a crab, there's a butterfly, there's Drosophila, there's C. elegans, worms, any organism. They have symmetries and asymmetries. And often on the outside, it's more or less symmetrical, but there's clear and highly conserved asymmetries in most organisms on the outside. But when you go into the inside of the organism, there are vast asymmetries that are required to be asymmetrical. All of the internal organs in any of these systems have to be asymmetric to work properly. So the question that's been around since Da Vinci is, how do you get these asymmetries? How are they set up? How do you take a symmetry? We break it into asymmetries. I mentioned to you the single cell egg starts out symmetrical and breaks symmetry. we've come to understand how some of that works. Something that led to a Nobel Prize for Hans Stemmen in 1935 was to use amphibian eggs and take that one group of cells in the early amphibian here and take a hair loop and divide that group of cells into two. And what he found is you get one animal and turning them into apparently two animals and joint twins, not fully separated. If you separate the cells very early, an earlier controversy in biology at the turn of the century, in the 1800s, took individual cells and separated them and made multiple. Well, were they also studying that? Falkenberg took this experiment, looked at the left-right symmetries inside of those two separated organisms, and very interestingly found that the twin that's on the right side had a very high frequency or randomization of left-right patterning of the part of the gut. On the left side is two. Always had them proper, the normal left-right symmetries for the heart. Yeah. And so that was a striking observation that literally sat in the literature until the 1980s. In part because it was 1919 when Falkenberg was a student and he died in the trenches of World War I. And the story kind of dissipated. Myself and several other people came into the field in the late 80s and early 90s and really restarted that field by studying what's happening. And this is a brief overview of many different labs, really hundreds of different labs, and how we think about how left-right patterning and the decisions are made in vertebrate animals. So very diagrammatic. Imagine this as a sheet of cells. Sometimes it's a ball, sometimes it's a sheet. The way that what happens is the cells move all over the place at the coordination level. And those movements set up the decision as to what side is going to be the head of the animal, what side is going to be the tail of the animal. And then an outside observer is looking at it going, well, I can tell that's the right or the left. But the cells on the right and left don't know that they're supposed to be right or left cells. Oops. They have to get that information somehow. How is that broken? It's a lot of the symmetric structure. What it turns out is a bizarre thing that really fell on accidentally. Note that there's a very small group of cells down here. What's going to be the tail of the animal? Those cells get very highly organized. They each have a little cilia, which is a little structure sticking outside of that individual cell. All of those cilia are like hairs, and they make an asymmetric fluid flow across, not in them, and across the top of the animal. So that fluid flows from one side to the other, one side to the left, one side to the flow. That fluid flows and picked up by cells on the side, throws a switch. And there's a series of genes that are then turned on, so the bucket brigade approach that march from the tail of the animal all the way to the head of the animal. Signals turn on genes on the left side, but not on the right side, and that is the first markers. On the right side, knowing that they're different. Interestingly, then, those sets of information transmit to what is just a group of cells at this point, that will become brain cells to tell them, when you become a brain, you're going to be a left brain. Same with the heart. When you become a heart, you go from heart to symmetrical bands and flows. So you get the kind with the same coils, bands, to liver on one side, and all that. So we called this thing the left-right. It's organizing the left-right pattern of all of the tissues that will eventually arise from this group of cells. Call it that whole animal. So the animal is very holistic beside. This is just a video of that. We found a small little vessel at the tail of the animal. It was discovered by in the late 1800s, and it's that just unknown in the literature until we started looking at it. We looked at it with microscopy and stuff that was available at the time. See the little cells, that little vessel at the base of the tail. And when you put beads into that vessel with a little microscope, microinjector, you can see those beads. There's an asymmetry that's full cells on this side, and detecting that mechanical movement transmitting a set of responses on the website. Really beautiful structure that the rest of the organism has organized and is setting up to help decide which is going to be the left and which is going to be the right. We then took that, we built a consortium of scientists around the country that were gathering genomes from kids who had congenital heart disease and their moms and their dads. And we hypothesized that if there are genes that affect that machinery that I just told you about, that build cilia or build the ability to detect cilia or respond to cilia, that there's going to be a lot of dysfunction in those genetic networks that are going to result in kids having heart problems, because the heart starts as a tube. If it doesn't tie itself going from symmetry to asymmetry into a knot, you're going to have congenital heart disease. 1% of all kids die from congenital heart disease. It's the main killer of kids in the first life. And we found that a lot of the genes that we discovered that were causing problems, so many genes that we think are causing those congenital diseases. So thinking about embryos and thinking about how this happens, there's a series of principles that help us understand the biological organism and help us think about human dignity. The first is, and we've talked a lot about what is an organism, what is an entity, what is a unit. For biology, an organism, it shows these 4 characteristics: integration, autonomy, adaptation, self-regulation, and development. So integration is really, this is a thing that is working as a whole that is greater than the sum of the parts. There's global integration. Setting up this left-right pattern across the whole animal requires all of the cells in it. There's autonomy, and that's self-directed internal regulation. It doesn't need instructions from the outside to do what it's going to do, whether it's development or health. There's adaptation and self-regulation. The entity actively alters its internal mechanisms, molecular, physiological, whatever, in response to outside stimuli or outside environmental change. And I'll touch a little bit upon that on the next slide as well. And development, this whole process of a single cell that's fertilized human zygote becoming a whole human organism. That's an internally driven process that we call development. So biological regulation, regeneration of asymmetry is another fascinating thing that I want to call out. And that there's many examples in the biological world where, and we mentioned briefly earlier this morning, where you can do some pretty nasty things to an animal and it will regenerate, and it will regenerate back to the normal structure. And so if you, this is just one of many animals that study that you can cut off a leg and an arm and it will grow back. And what's interesting, and we're starting to understand what are the mechanisms, what are the molecules, what are the genes, blah, 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 that are required. But what we really don't understand from a larger level is how does it grow back to the same size and shape and proportionality? Right? We really have no idea how that happens. We don't know how it happens in development. And we really don't know how it happens in generation. In my own lab, we can take a zebrafish, a small fish, we can cut off a third of its heart. And it wakes up from the surgery, swims around, and 30 days later, you come back and you can't tell where you chopped off that third of the heart. The animal regenerates that heart in very fascinating mechanisms. They require it to reorganize and redo all of these things that its cells are doing. An extreme example is a planarian. You take one green animal, you cut it into lots of bits. And each bit will regenerate with all the body in the head. The head part and all the time in the body. There's an internal ability for that thing to reorganize, redrive itself, and reform that same shape. So we know how to mess that up. We know how to block the genes and the molecules and the signals that do that. But we really do not understand how it gets back to the same size shape. So those are big questions that really help us think about the biological aspects of human biology. Third and final part. Pope Leo XIV specifically calls out universities. So we're sitting in universities, comfortably doing our university things, right? And he really says, at the same time, I would like to encourage academic institutions and universities to give fresh impetus to these principles, the 5 principles that I outlined earlier. and quote, to apply them in a way that will be relevant and effective in addressing the digital police. And he notes that, quote, all teaching, research, and innovation should be guided by the foundational truths about the dignity of each person and the good of all people. So really laying into those five principles and telling universities to get at it. Emerging technologies provided unique opportunities for evangelization. So he says, quote, indeed, we must consider the digital world as a new continent to be evangelized, one that requires generous missionaries who are mature in the faith. So we're called to found people and have those students and people really be missionaries into this continent of evangelization. And the rapidly evolving questions of the existence and behavior of artificial intelligence. We hear a lot of this about when is AI going to have consciousness, when it's, and there's all kinds of questions that you're all familiar with. The beauty of that questioning is happening everywhere. It's not happening just in people's space. It's happening, and it's having very strong social ramifications that are driving secular humanists, transhumanists, atheists, technologists, and really a wandering generation in this space to ask the big questions. And that is an opportunity for evangelization. The big questions are being asked. The Catholic Church has spent a couple thousand years sorting those out. And I think we have an opportunity to bring things to the rest of our society in evangelization. So we at the university take that very seriously. We started, when I first got there, I walked around and found that there were many people doing things on artificial intelligence and other emerging technologies like some of the biology I've talked about. And I said, let's get this put together. I started a new institute at the university, struggled with how to call it. As soon as Pope Leo came out saying, I'm the next Pope Leo, we said, I got a guy out in the statue in the hall. We're going to call it the Leonum Institute. So my high school Latin, I think Leonum means of the Leos. So we're having at least 2 Leos lean into this. And so it's an institute for AI and emerging technology. And really the goal is to align AI with human dignity, truth, and the common good. We're advancing human-centered AI really about the virtuous and ethical use of artificial intelligence and other emerging technologies. We're advancing AI-centered, human-centered AI through the lens of Catholic anthropology, really thinking about the whole person and the dignity of the person. We're merging the formation of students with rigorous research and with venture capital creation to shape technology that serves human flourishing and the anchors that were founded in the Catholic principles and Catholic universities. So the Institute is driving research and a lot of these emerging technologies. We're really leaning into the formation of our students and how they respond to and deal with the emerging technologies, teaching them not only about AI and how to use it, but other things, really leaning into our School of Philosophy and our School of Theology to help us handle integrated ethics. And then we're leaning into innovations. The Institute does hackathons, we have fellowships. It's very much important doing interdisciplinary across all the schools and colleges. We're building a mentorship program and we're building things in studios. So we're equipping the students and eventually evangelizing out to the public the ethical and masterful use of artificial intelligence. I've already mentioned some of these activities across the university and beyond, but we really see ourselves as a conduit. We can't do everything at one university. And we really want to partner with other universities, other institutions, other corporate groups to help us move forward with this space. So I've been very blessed. My office motto is Dominus Providebit, which means the Lord shall provide. And I remind myself when I recite that to myself, it doesn't tell me when he's going to provide. It doesn't tell me how he's going to provide or who he's going to provide. But he has definitely provided some really outstanding people to this effort. One is Taylor Black, who many of you know here in the room. Taylor is at Microsoft, and when I was talking to Taylor about this thing we're building, he got very excited, gave us a lot of advice. And I realized that as a university, there's no way I can hire a guy out of a major hyperscaler. But Microsoft has this weird policy where they give their people 30% of their time to do moonlighting. So Taylor is basically moonlighting for the Catholic University with a good chunk of his time. And from my, apparently, it's 30% of like 120 hours a week of his time. He's really under it. And he's really helping us lean into this artificial intelligence myself. We just hired the guy, Matt Gardner, who is helping us build a venture studio and a venture fund. This is a unique part of the thing that we're building, is that it's an institute outside the university. It's not owned by the university. It's a separate space. It's a separate seat. And it's a venture studio. So we're taking all the intellectual property that's being generated by our university out of this research space, and driving it through the system to commercialize. And that's one of the ways we're going to be funding this institute activity. The other thing is that we're looking for partners at other universities who maybe don't have the time or bandwidth to start up a venture studio, commercialization studio. We partner with those universities to drive this effort forward. Other Catholic institutions and other institutions as well. So really looking for partners there. And then Alexandra just joined us 2 weeks ago. She has a PhD in anthropology and religious studies, so she's cued into that. And she's really helping us do a lot of program building in this space. So it's a small group right now. We're building out. We're very much looking for partners. This is a slide on the capital ventures thing that we're doing. I'm going to skip it for want of time, but we're really just kind of building things and getting them out into the world from the venture stage. So as I mentioned, our research motto is Dominus Providivit, and I'm hoping that part of what he provides are good partners and good collaborations with other people outside our university. So that'll take questions. There's a couple of ways. You can just Google Leonum Institute, or my email or my office email is very easy to remember. It's research@cua.edu.
Written on the screen.
But please do. I mean, we're very interested in working with people who are interested in these technologies in the education space or in the technological space.
Next question. Please. I ask you the same question. So what do you think the life principle is based on your symmetry experience?
The answer, as Father Guy reminded me to say, is I have no idea. I'm sorry, Brother Guy. But I mean, there's clearly something going on there, right? And we've known that since cognizant humans. And there are these, you know, not being a philosopher, the worst thing of a person who's not a philosopher is a biologist who thinks he's a philosopher. That usually happens in a pub with a pint. But I really don't know. I mean, that we're describing what life is. We're trying to understand what life is, and I think the most important thing for us is to really call out the things we don't understand. That we don't even, as we heard earlier conversations about what is next in quantum. These big questions about how does an organism form itself during the developmental process, right? That's a unique aspect of life. You don't see rocks form themselves. Are there physical particles that can reproduce and form themselves or reform themselves? Depends on how you define it. And so that ability to develop, those principles I call it, the ability to develop, the ability to self-regulate, whether it's to develop as an organism or to grow an arm when you cut it off. Those are principles that tell us something about life, how it's made, how it's put together. I mean, the idea of an organism, my disclaimer, my wife, Maureen Convick, is a bioethicist who's written a lot on what is an organism and what does that tell us about what is a human person. But that organism from the first cell throughout when you're dead, is an entity that can be defined as a biological entity. So the organism is very much the soul of that living thing. Its ability to organize.
Yeah, I agree. I think that that's the way forward. Stop abortion. Realize there's more to it than just world aspect of it.
It's the organization, the way it's the organization. Intercultural way talks about when you take frog and put it in a blender, it's still a frog. Yeah. All the molecules are still, but they're not properly put.
And this means that implies an intelligence.
Absolutely, in some way. I mean, I want to be careful. We've already misused the word intelligence and artificial.
Yeah.
I want to be careful not using it biological. Something wrong. Something else.
So you tell us how these very simple organisms can regrow parts of themselves.
Yeah.
So obviously, we can't regrow parts of ourselves.
Right.
So in complexity, what's the most complex animal that can regrow parts of itself?
Right. The most complex animal, well, I mean, human beings actually can do regeneration. People are doing surgery on fetuses and their ability to do wound healing. We all do wound healing. There's some better or worse, not some better ones, but really to do major reorganization. The mammalian fetus still retains that possibility. The mouse, which is pretty close to humans in some ways, I'm not as furry as they are, but they can regenerate their hearts in the first 5 days of post-birth. And so a lot of the regenerative ability we think is actually lost in the quote higher organisms. It may have been there evolutionarily, it's dissipated for some other reason. You imagine like using those mechanisms to get you in trouble as well, from down cancer. So it's available in higher organisms too.
Do you think that the fact that life has a well-defined chirality is a signature that or a proof that there is a single origin of life on Earth? Life on Earth has a common origin.
Does life on Earth have a common origin? I would say most likely, because the underlying structures of most organisms are pretty highly conserved from an evolutionary perspective. So we don't, to be extreme, we don't see silicon-based organisms. We don't see the underlying molecular processes are fairly conserved. The underlying genetic tools that are used in the developmental process are pretty highly conserved across all organisms. When you dive into different kingdoms, the plant kingdom, yeast, even some of those networks and pathways of decision processes as an organism takes pretty high conserved. So we could find an organism that does things a little differently, but we have not yet. So that would suggest that it's all come from a single source, evolved out from that source. But it's uncertain at this point.
Why don't we thank Dr. Yost?
So it's my pleasure to introduce our next speaker. Javier Sanchez Gonzalez is a researcher in the Mind-Body Group at the Institute for Culture and Society and a member of the Science, Faith, and Reason Group at the University of Navarra. He holds a PhD in physics from the Universidad Autónoma de Madrid and a PhD in theology from the Pontifical University of the Holy Cross in Rome. Since 2005, he has been teaching at the University of Navarra. And as of 2022, he is an accredited full professor. So his interests revolve around the intersection of science and religion, the philosophy of nature, and the significance of quantum mechanics and understanding human uniqueness in the universe. And he's also a member of the Society of Scientists.
Have some echo.
Mute your speaker and your microphone.
Otherwise, you will hear yourself twice or more.
That would be awful.
today is Beyond Physical Closure. So happy to have you, Javier.
Okay. Oh. Thanks a lot, Andrew and Vincenzo and Chapman University, the organizers. And so let me begin my talk with story. Okay. So like 10 years ago, I was in a meeting like this, a conference about physics and ontology. I was going to attend a talk by Toft, maybe it's not most of you. And a young Canadian postdoc approached to me and said, so, guy, your dress code is a bit weird. I was dressed like this. So he said, are you something? Are you a minister? Are you? And I said, yes, I'm a Catholic minister. I'm a Catholic priest, actually. And he said, okay, so could you explain to me in 5 minutes what you Christians believe with my language, the language of physics? Okay. And I said, well, 5 minutes. Okay, I decided to speak about God and Jesus of Nazareth, and that was it, 5 minutes. So when I finished my small presentation, he said to me, okay, hang on a second. So you Christians believe that the fundamental gauge symmetry of the universe is broken in Jesus Christ.
Close enough.
And I'm telling this, apart from keeping you lively and awakened, is because it inspired me about what I'm trying to do today, and is presenting, or at least trying to make more palatable to scientists in general. Maybe I'm a bit biased towards physics, to physicists, what we believe, but also, well, something that's very fundamental in my view is this question of different kinds of causality, and particularly the space, the possibilities that we have to have immaterial causality. And so this will be clear as we advance in this talk. I would like to mention Elaine Eklund, who is a sociologist of Rice University. So she knows a lot about what scientists really think. It's a nice book about scientists, and she also wrote this article, this paper, about scientists around the world. She interviewed, like, I think more than maybe 1,500, 1,800 scientists. So N is 9,000, but maybe the answer were only given by 1,800 scientists. So the question is, what she shows in this paper is that on average, scientists are less believers. So they believe less, and in terms of belief and practice of religion, they are less believers than the society in which they are immersed. So she focused on 8 countries, especially in Western countries, so France, United States, UK, and Italy. So scientists tend to be less believers. And the question, there's a reason for that, and she explains this. So the reason is that scientists do not believe that there is a conflict between science and religion. It's a matter of indifference. So religion becomes invisible to them, or they have this indifferent attitude towards religion, because science gives them all they need in order to cope with life. Okay, you understand this? So I think that, at least to me, this gives us like a warning about this, we could call it, the separability of science and religion, or the famous non-overlapping magisteria by Stephen Jay Gould. He spoke about non-overlapping magisteria. But okay, you can do that, and maybe it's a good movement initially, but yeah, so beware, choose wisely, because many people are saying, okay, yeah, separate realms. Okay, so I go for science. I don't care about religion. So it provides nothing valuable to me. So I think this is a problem. And I think that part of this problem is that throughout history, there have been some misunderstandings in what science is about. And I would like also to spend some time speaking about these misunderstandings. One of these misunderstandings is that science is just about the material world. And this is one of my favorite questions. So you speak about matter. What is matter? What is matter? Something that has partes, extra partes. That's the beautiful definition in medieval philosophy. And well, we know that the basic building blocks of nature, quarks and leptons, are point-like particles. So where are the partes, extra partes? And what about, space-time itself that can be treated by physics? So I think that the reference to materialism or to matter is a bit outdated, and the threat today is what I would call physicalism, at least in philosophy, in analytic philosophy. The interpretation that thinks that everything is material now has become physicalism. And physicalism answers to a dogma, which is the physical causal closure of the cosmos. So this principle can be stated as follows. Every physical effect has only a physical cause. So this is physicalism to go. Okay. And well, I think that's a problem. I'll try to overcome this position. But there's a second misunderstanding, is the question that science is just about measurements. Come on, guys. How can we ever say this? So measure has to do with establishing proportions, and proportions are very useful to establish correlations. Through correlations, analogies. Analogy means how I climb this ladder of knowledge to get a new knowledge. So we do that in order to know, for instance, that mass and space-time are correlated, Einstein, or that temperature and extension of some iron bar are correlated. Or, for instance, nowadays I'm working a mind-brain group in Navarra. So I'm working in what is called scientific theories of consciousness. So scientific theories of consciousness think that there should be some correlation between the conscious processes about the neural correlates that sustain these conscious thoughts, conscious life that we have. And that's why it's possible, at least, to approach this field scientifically. So we could discuss a lot about this. But my point is that science is interested in all reality, all reality. A different matter is the question of the method, but it's interested in all reality. Remember Father Tanseranity, he claims that it's general, the material object in philosophical terminology of science. Okay, so well, I think these are things that we need to overcome somehow, and I'm going to deal now with this question of causality, different kinds of causality, and especially how can we recover this idea of immaterial causality. And this is very important, especially for the question of the soul. I think that's a really big issue for Christians. So the soul, and let me tell you that this is in a nutshell, but the problem of immateriality doesn't start with Christianity. So in the Greek philosophy, we have the problem of the body-soul interaction. Soul can have different meanings. So every animate being has a soul, but we find that in the Greek world, in the Greek philosophy, there are like two approaches. I would like to call one of them the Platonic Aristotelian approach, that basically says that the soul is different from the body, so cannot be reduced to something bodily. And there's this Stoic Epicurean approach in which basically the soul is bodily somehow. But okay, if it is bodily, then how is it different from the body? If it is not bodily, if it's immaterial, that broad sense, we have the problem of the interaction between soul and body. I think that Aquinas is a good, helps a lot in this question, because he says that, for one, that this union between soul and body is not accidental, and the soul gives being to the body, and the soul does that through formal not efficient causation or causality. There's a tension here in this view because what we are saying is that the soul is the substantial form of the body, but at the same time, so naturally it's the substantial form of the body, but at the same time, after death, the soul subsists in itself. So, yeah, I think that all of us perceive that tension. So how can this be? Because in nature, these substantial forms disappear when the material bases disappear. So what's going on here? How should we understand this? And I think that, it's important trying to offer some new insight or explaining better what we mean by this. Okay, just to give you an example, because I think this is, at least in my feelings, mind-brain field, this is important. Carlo Rovelli, pretty well known by all of you, and he says in a dissemination paper, consciousness is not separate from the physical world. Our soul is of the same nature as our body and any other phenomenon of the world. So is this true? In what sense is it true? Is it not? It's not true. What's going on? I think this is an important problem. And I see this every day in this work, in the philosophy of neuroscience. Okay. So, in the second part of this talk, I would like to explain a bit how come this view of causality, of immaterial causality, is so difficult today. And a good way of approaching this problem is provided by John Hedley Brooks. John Hedley Brooks is a historian of science, and he has a beautiful book about science and religion, the different relationship between them. And when he explains the origin of the modern science, he claims that there is a shift in the explanatory logic, and we shift from the metaphor of the organism, that's antiquity, that's medieval age, to the metaphor of mechanism. And this is beautifully illustrated in these two different quotes by Leonardo, the last of the medieval thinkers or polymath, and Kepler. Leonardo says, we can say that the earth has a vegetative soul, and that its flesh is the land, its bones are the structure of the rocks, its blood is the pools of water, its breathing and its pulse are the ebb and flow of the sea. So, you see the explanatory logic. I'm comparing with an organism. Now, let us listen to Kepler. I'm much occupied with the investigation of physical causes. My aim in this is to show that the celestial machine is to be likened not to a divine organism, but rather to clockwork. Moreover, I show how this physical conception is to be presented through calculation and geometry. So it's a different explanatory logic. This happens with science. So, and this explains, I think this has appeared in this conference many times, that for many people, physicists included, causality is physical causality, so that means material and efficient causation. So formal and final causation are out of the question. So that's, of course, Francis Bacon, but I think that the idea is clear. But let me go a bit deeper in this view of John Hedley Brooks, explaining how this mechanistic view populated the thinking during this century, 17th and 18th centuries. He explains, we have here 4 scientists, all of them believers, Marie Mersenne, Descartes, Robert Boyle, Isaac Newton. And what happened is this, I think it's beautifully explained, that we have a new theory of matter, a new theory of causality, a new theory of method. A new theory of matter, in that the ultimate components of things were particles stripped of qualities. So no longer qualities. So it's just movement and structure of particles. So color, taste, smell. So it's reducible to this movement of particles. A new theory of causality was stressed, whereby contact action, the mutual impact of particles, became the paradigm case of causal agency. Billiard ball causality. That's it. That's the new paradigm. That's the explanatory logic. Why should we need something like formal final causation? It's no longer required. So you see the problem. So, of course, and I think it's pretty obvious to us, we've been discussing these things these days, that there are clouds in this horizon, this mechanist horizon. Some clouds have to do with chaos theory or with complexity theory, and of course, quantum mechanics. One of the clouds, I think, is thermodynamics. Thermodynamics is very interesting. We haven't still solved the problem with thermodynamics. One of the most basic laws of nature is an inequality. We've been talking about Bell inequalities. What about entropy? How do we explain the best directionality in this law? Why this happens? Statistical, well, you need a past hypothesis. You need to assume that the entropy at the Big Bang was extremely, extremely low. So why is that? It's by hand. Anyway, okay. So of course, well, this is a beautiful estimate by Penrose explaining how special our universe is according to calculation about the entropy of black holes. Not going to technicalities, but the point is this is a huge number. So our universe is as special as 1 part in front of 10 to the power of 10 to the power of 123. Actually, it's 124. Okay, doesn't matter because you cannot write down that number at the scale of the universe with zeros, 1 centimeter of extension. So Penrose claims that this is the most profound mystery of cosmology. We don't have an answer for that. Anyway, I think these are clouds in this mechanistic horizon. And of course, the question of quantum mechanics, I won't spend time on this because we've been talking about quantum mechanics all the time. We have the deterministic Schrödinger equation. We have the reduction of the wave packet. Today, we had a good question. I think that it was Valerio who said that, so how does nature work? How does nature determine itself? So that's a real question. And we don't have a good answer for that. And this transition between the quantum world and the classical world is fuzzy. We don't know how that happens. We don't know even if that happens. I mean, is everything at all levels quantum? Or there is some level at which we recover classicality? For instance, because Bell's inequalities are not violated, or they are an equivalent of Bell inequalities that are Leggett-Garg inequalities, are correlations in time, that they are looking for macro realism. It's a project of looking at which scale quantum mechanics stop working. We don't know. But the question is, this is fuzzy, this border. So, because there is no a criterion or a scale for catness. If you think of the Schrödinger cat. So when a cat is a cat, a macroscopic cat, well, reference to H bar or to action is no help because that depends a lot of the model you are using. So well, the transition from the quantum world to the classical world is not universal. So it depends a lot of the model that you are working with. It's different in the case of relativity. So C is universal, and we have this V over C criterion. When it's much smaller than 1, everything is smooth, and we come back to Newtonian mechanics. So what's going on here? I'm entering the third part of my talk, and I would like to spend 2 slides speaking of epistemology. So let's step back and think a bit about how science, how scientific models, how scientific activity is actually done. I would like to catch your attention and think with you about these 3 questions. The question of external conditions, initial and boundary conditions that are required in order to obtain the right solution of a differential equation. So differential equations have many solutions, but only one of it is actually realized, physically realized. So we need to invoke these external initial boundary conditions to get the right solution. So why is this? Why is, I mean, epistemically, it's not at all justified. So I was remembering now Frank Wilczek, who says that this is a sort of drawback, because we are very good explaining the dynamicity, the dynamic laws of the universe, but we still don't have an explanation for these external conditions, initial boundary conditions. Lee Smolin, for instance, speaks about the physics in a box. We work always as if we were using physics in a box. So we have always a system and environment. This distinction has something of arbitrary, at least if you are only thinking in physical terms. So why this system and why this environment? So I'm trying to land my theories with a model, but still why? Non-linearity, or the question of phase transitions that we know happen in nature. And these phase transitions many times are responsible for the appearance of non-linear terms in equations. So Schrödinger equation is linear, but we have non-linearity, especially think about Navier-Stokes equations. So weather prediction is very difficult because of these non-linearities, and many times because of the mixing of scales. So we have parameters, for instance, viscosity, that is a sort of integration of many other parameters that we need to put into the equation, and then we obtain at least an approximation to the dynamics. So how this happens? I mean, you can think about you are doing some limit, you are making some simplification, but is this telling us something about the ontology of the world? What's going on? And we've just heard before lunch about symmetries and symmetry breakings. So we physicists like to explain things. The new explanatory logic is symmetries. Okay, but the universe is not symmetric. There are symmetry breakings. So why this happens? I mean, what's the reason behind these symmetry breakings? What's the ontological cause behind these symmetry breakings? I think that Bernard Lonergan can be helpful here, because he says that there are things that science cannot explain. And this is the particularity of many systems. Let's think about this. We derive this conservation of energy, of momentum, etc., so on and so forth, with symmetry assumptions, so that there is symmetry, there is temporal symmetry or spatial symmetry. But that's not true. So actually, it's not true. So in the universe, we have the time symmetry is broken. So it's not the same of doing an experiment now than 5 million years ago. So I guess not, or 5 billion years ago, well, the Earth didn't even exist. So these sort of things, I'm just trying to give you a glimpse. So the symmetry breaking with this Mexican hat, I think, at least to me, it means that the principle of sufficient reason, that we are looking for the right, I mean, the set of necessary causes that become the sufficient cause to explain a phenomenon, is never reachable by science. And in practice, what we do is working with this ceteris paribus condition. So we control a system and we say, well, with the other variables, making more or less the same things. So we make some integration, we trace them out or whatever. So we focus on the relationship between this variable and this other variable and see what's going on. And we obtain a deep knowledge with that. So we see this structure of correlation, of causation in the universe, but we cannot assume or say that this explains all the causality that it's present in the explanation of the phenomenon of interest. So this is a strong metaphysical claim that more or less has been done during these days, and I also embrace as the question of formal causality. And my point is this, that formal causality, so the bearers of formal causality, provide the immaterial, and this is important, I'm gonna justify it now, the immaterial causality necessary for the emergence of these specific particular individual systems in nature. Okay, and the mathematical correlate of that is symmetry breakings, constraints, external conditions, scale mixing. and that forms constitute the principle of natural individuation. So in this sense, I move apart from the Thomistic view, and in this question, I'm closer to the Scottish view of the principle of individuation, but that's a topic for another talk. Okay, but so I'm saying that forms are immaterial because forms are not material, because material is the material cause. Even though in nature forms are materialized, are present in matter, but forms cannot ever be material. That belongs to the material cause. So of course the question is how is this possible? And hylomorphism helps a lot in this, saying that, well, sometimes this is a fundamental substantial relation between material cause and formal cause. Okay, but the question is that I think this is not enough, but can help to explain what comes now. So fourth part of my talk, let's think about the evolution in nature and how things have been appearing in nature. And well, I like this picture because you see the variety of beings, of living beings. These are all the species. With humans, I think we are over there, the far right. And one question is, so there is novelty in nature. So by novelty, I mean something that is really new. So it's not just a mere different configuration of particles in a background space-time. So there are new properties, emergent properties. So I'm saying I'm embracing the view of strong emergence. It's not merely epistemic emergence, so something that appears to be complex or appears to be new, but ultimately can be reduced with a big effort. So we don't do it, but could be in principle reduced to the basic components of reality. So the question that we have this novelty, this rich variety of things in nature, and this happens, I mean, thinking as a physicist, because we have successive coarse graining of degrees of freedom in nature. What is coarse graining? Well, actually, we don't know what are the fundamental degrees of freedom of nature, but we know that many times what happens in a phase transition is that the phase space of the microphysical degrees of freedom is reduced because there are new properties or new degrees of freedom that now take over. Now they take control. So just think about it's like a reduction of entropy in the microphysical phase space, but with that we obtain a new degree, a new set of possibilities. So Stuart Kauffman explains these things, explains about the impossibility of principle to predict evolution. Have you ever thought about this? We cannot predict evolution. Could you predict evolution from the Big Bang? I mean, specific emergence of this species or this other species. So we can make some statistical predictions, general predictions, but we cannot say when this specific system or this specific animal is going to live in the world. So coarse grain, I think it's an interesting way of thinking because, well, this is more or less the definition. This has been done with ChatGPT or Gemini or Claude or whatever it is. I don't remember. But it's the idea that we have some rule by which some number of microphysical degrees of freedom belong to the same or form the same macroscopical degree of freedom. Typical example is gas, where we have these emergent properties, pressure, temperature, volume, whatever it is, that can be realized, can be multiply realized in the microphysical phase space. But my point is that this selection rule is not microphysical, doesn't come from basic physics. So it's something that happens, and we don't know why that happens. There could be many different coarse grainings with the fundamental laws of physics, but we have only some of them. Why these ones? So selection, if you think about what is selection, is a procedure that is not material, and it has causal influence. So what we see is that like this, this is how the universe, how nature is going itself, is harnessing itself towards more complex structures, but also new degrees of freedom, this novelty. So what I would like to say is that perhaps this idea of degrees of freedom could help us understand the novelty of what the human being is in nature. I think we have a challenge here. So in a sense, our explanation has to keep the continuity of the human being with evolution. I mean, the human being is nature. It's not beyond nature. It's nature, comes from nature, comes from evolution, period. And I think I would say comes totally from evolution, comes totally from God. These two things. So how can I explain continuity with the exploratory logic of evolution and discontinuity, especially in the question of the subsistence of the human soul? So what happens here? And I think that what we have is like a sort of inversion of this coarse-graining tendency of nature, where we go from microscopic phase space to other phase space, where we have new degrees of freedom, but all of them have a relation of n to 1. So n microscopic degrees of freedom correspond to 1 degree of freedom. But what would happen if at some point the mapping is not a mapping, it's a correspondence. Instead of having n to 1, we have 1 to m. What I mean is that perhaps to a specific neural state in the brain corresponds different mental states. We will have this inversion of the coarse graining. So there would be like a fine graining when the human being appears. And incidentally, I would like to say that how to understand this emergence of new degrees of freedom, mental degrees of freedom, do I have a way of distinguishing these new degrees of freedom from the physical degrees of freedom? And I would say that what distinguishes is the causality that they exert. And in the case of physical degrees of freedom, this causality is always limited by the speed of light, as Valerius has pretty well explained this morning. So the speed of light is the limit for causality in physical things. But in mental things, I don't think we have this limit. So mental states can have this causal effect relation in present simultaneously. So, but it's very difficult. I don't know how to show violation of Bell inequalities or Leggett-Garg inequalities in mental states. Maybe, well, I don't know. Okay, so that's a way how I would try to explain what we Christians believe about immateriality, the human soul in the universe to a scientific colleague. So if I have time, I think I still have 5 minutes time. I would also like to speak about the divine action. That is the other difficulty that we have in explaining what we believe. I understand when we say that God is transcendent, of course it's true. God is beyond nature, God is beyond creation, it's the creator that is beyond creation. But at the same time, God is immanent to creation. By immanent to creation, I mean that God acts in the world. So how can we explain this? Because, well, the problem is if God is acting in the world, well, it's doing like it's like a put-up job. So it's a bit of, why didn't you think that before? Why you need to do a miracle? Well, think better next time. You know, I'm trying not to be. It's difficult to explain many of these things, and I think that here it can be useful to think better about the concept of creation. So first of all, I would like to explain these two problems about the action, the divine action in the world. So for one, we have the problem of unity and plurality or multiplicity. How many creations do we have? If you go to the scripture, there's also a tension between the creation and action of God that are also creative. So there's unity and there's plurality. And there's also the tension between general divine action and special divine action. So general divine action is providence, so it's the general care that God has about the creation. But there seems to be special divine action in some miracles, in some specific action of God. And I think all this, that it's in a controversial relation, can be understood better if we go to the concept of creation and we understand better this concept of creation. So what I'm saying, or what I like to say, is explained very well by Professor Tanzelaniti in this entry creation in the interdisciplinary Encyclopedia of Science and Religion. And when we speak about creation, we're speaking in these three senses. The active sense, in which creation is the act of God creating, the active sense. We have the passive sense, that is the result, the effects of this creative act, that is one. There's only one creation, but we experience many times with many different levels this creative power of God. But there's also this grounding relation that means that creation points to the fundamental relation that creatures have with the Creator. So my point here is that, so if this is so, of course, we could understand this saying that there is a primary cause, the fundamental transcendental cause, God himself, and then secondary causes. But it's very important that we articulate this relation between the secondary cause and the primary cause or the transcendental cause, because otherwise, I mean, for a scientist, or I would say for anyone, if God is just the transcendental cause and there are no traces of God's action in nature, well, I think we are betraying this transcendence and immanence of God in his creation. So I think we need some work here. Maybe theologians are required to do a better job here. But if we manage to understand better creation, we can also understand a problem that has to do with the presence of evil in nature. So I'm going a bit fast, but the question is that evil is also one of the problems in making understandable a concept of God in nature. So how come a good God can accept or can allow for the presence of evil? So is evil something that God wants, that God allows? Why is this here? So the question is, if we think about the development of creation with this binomial of determination and indetermination, we could think that the events that are going on, well, each one has its own identity. Some of them are evil, that we experience as some irrational or unexpected indetermination. There's a full characterization of evil in the literature about theology. But the question is, if we understand creation as a unique act of God, then we come to understand that it is the eschatology, so the end of time, what gives the right identity to each of these processes. Okay, so what could happen is that perhaps the eschatology, many of these processes keep more or less its identity, but at some moment, this evil, it's something that is better, it's not that evil. So, but we need to expect, or we need to wait for the eschatology, the last times, to get that done, because God is the eternal creator. So that means that we cannot see or we cannot understand the full development of creation until the end of times. And that's because of the very being of what creation is. And I think in all our explanations, when we speak about God action, we put God in time. And that's probably the main source of problems when we try to speak about this. So just since I'm running out of time, I would like to read a beautiful explanation about evil and about the role of theological virtue, of the virtue of hope, by Pope Benedict XVI, and we'll end up with this: hope as a fundamental attitude. So faith tells us that there are not two principles, one good and one evil, but there is only one single principle, God the Creator. And this principle is good, only good, without a shadow of evil. This is the good news of the faith. Only one good source exists, the Creator. Then follows a mystery of darkness, of night. Evil doesn't come from the source of being itself. It is not equally primal. Quite simply, evil exists. How was it possible? How did it happen? This remains obscure. Evil is not logical. Only God and good are logical. Logos, Father Guy Consolmagno. Evil remains mysterious. The biblical image cannot explain what is itself illogical. We may guess, not explain, nor may we recount it as one fact beside another, because it is a deeper reality. It remains a mystery of darkness, of night. But a mystery of light is immediately added. Evil comes from a subordinate source. God with his light is stronger, and therefore evil can be overcome. So I think this logic is the logic of hope, the logic of how God ultimately justifies himself in eschatology, is also present in these lesser problems of determination, indetermination of process in nature, and how this articulation of causes cannot ultimately explain the identity of things and processes, and that's why perhaps we need non-local forms, Valerio said this morning, non-local forms that are ruled by a final cause. So thanks for your attention, and open to QA. And someone can tell me the result of the semifinal? 2-0, so good news.
Okay, we did not expect moral theology, but it's great to bring that into the equation here.
So maybe Vincenzo, you want to start us off?
Thank you. Very, very nice talk, Father. I would, I guess coming to this question of the eschatology and now the zero back from eschatology to evil, and trying to understand better is you said something on the line that maybe it's not that bad. I didn't understand well, but maybe I don't understand better the way I understand. That I completely agree that is outside time. So everything is eternally present in him until the end of time, right? But nonetheless, that he does so the evil as a privation of good comes from its permissive will, right? So one can still think about the logical step even in beyond time. So he doesn't will it in the first instance, but because of freedom, he allows it, and therefore it's not that there is a goodness, any goodness in that. Is that in a sense he's ultimately is able to provide goodness even in an instance where evil is permissibly allowed, although not willed in the first instance. I would say not in time. I'm speaking. Is this what you mean?
There are many things there. I would like to clarify first that God is in time as the eternal God. So how eternity is in time, sustaining, underlying time. So God is the eternal presence in every moment of time. Okay. But at the same time, so it's not that I'm explaining evil, so it remains a mystery. The question is that things, for instance, you refer to good and bad. And of course, there's a very clear ethical issue in which we speak about good and bad. But I think there's a deeper meaning of good and bad that belongs only to the Creator. You remember the fruit, the tree of the forbidden fruit? It's knowledge of bad and good, evil and good. Why? It's not good to know what's good and what's bad. What happens? I mean, the meaning, the whole meaning of things needs the full determination of eschatology. And of course, in many questions, I mean, in many situations, the identity is quite fixed. I'm thinking about saints, I'm thinking about good people. But there are other situations in which, there is something that it's deeply it's deeply wrong. So there's something profoundly missing here. And we cannot expect to understand that because we need to expect to the globality of the creation, the full deployment of creation, to understand the individuality or the meaning of individual parts of this creation. So how the whole determines the identity, the deep identity of things, and of course of living beings, human beings. In other words, we have to wait for what is going to have been. What is going to have been, if that makes sense.
Maybe just a further thing, this is related, if I may ask.
To you, Vincenzo, otherwise you go home.
A very, very nice talk. I was drinking from your house a little bit, but that was great. So I see a lot of people across disciplines, I would say, somewhat attached to this idea that there have to be either some process related to consciousness or will that is unexplainable by physical causes. And that would be the process that the soul is the, let's say, material cause or effect, cause for. The way you put it, I mean, I really like the way you put it, but I wanted to ask for you to put a fine point of that on that. So what you're saying, would what you're saying be compatible with the notion that even if all processes of, say, consciousness, for example, were explainable through just the material world, if I understand correctly, that doesn't present a problem to the soul being formal cause of it of it all? Yes.
There are two things there. So what you are saying can be defended, but we still run into the explanatory gap. So David Chalmers speaks about the high problem of consciousness, and it's what you've explained, that even though I have all the neural correlates and I knew all the physical causality with these processes that are the basis of consciousness, I don't have yet an explanation. And this is because, so explanations in biology tend to be functional. So if this is so, then this is so. And then if the heart does this, then we have blood going out. But the explanatory for consciousness is not that, because consciousness is not a function. It's something different. So we don't even have the explanatory logic. Additionally, what I'm saying is because of this mix of determination and indetermination in nature, because when you have something determinate, immediately I have an adjacent possibilities of indeterminations. I don't think that we can explain the brain workings only physically. So I think that there is a real influence, but not efficient causation or not material causation, but selection. What consciousness or what the mental degrees of freedom or the mental faculties do is select the right, at the moment, the right physical configuration of the brain.
But I would say that would be what is not explainable would be then what doesn't have a material cause. So something that is whose material cause can be pointed to could be pointed to, and that still doesn't, like, you still have this.
Right. If we had the knowledge of all the microphysical degrees of freedom of the brain, even if because maybe it's not only the brain, because it's the personal history, so it's also the interaction with the environment. So what are the relevant degrees of freedom? It's not clear. But even if we had that, we couldn't explain the emergence of consciousness, and we couldn't even explain the dynamics, because we would need additional causes, this selection process of this particular configuration, So still there remains some indeterminacy. So there's degeneracy in the processes of the brain that can be fully realized.
Another question? Yes,
Question about your notion of form. So you mentioned, of course, that forms can't be material because they're not matter. But do you mean that, and you focused a lot on human forms and mental capacity, but like in some ways, especially in the Thomistic framework, the human forms are special because they can survive the death of the body, whereas other forms can't. So would you say that like say the form of water, the form of a daffodil, are these things also immaterial in the sense that they are non-physical, right? Because according to like natural philosophy, as it was studied by medievals, right, these would be natural forms that would be studied by their version of physics. So yet they would be forms, not matter. So like, is that the type of immateriality that you're focusing on? Or are you focusing more on the type of immateriality that allows for the human soul to survive the death of the body?
I agree, these are two different types of materiality. And I believe, I'm not a Platonist, so I believe that the materialized natural forms disappear, or change. So there's a whole evolution of natural forms. But in the case of a human being, what we have is like the lift off of immateriality. But for a time, I mean, for some time, because here in this confluence of material world, the natural world, and the mental world, we have, this is like a recapitulation of the whole creation in the human minds. That's why we are expected to have our full materiality back in the resurrection. So if we want still to have relation with the creation as it is, material creation, so this cannot be lost.
Sure. I guess my concern is that it seems like the immateriality of natural forms might, on at least in some readings of your account, be almost supernatural, right? Whereas like the human form or angelic forms or angelic ways of being, which are really just formal ways of being, seem to be of a different order, not entirely measurable. And so like this would come, you'd have a problem with like this is the Chalmers has a problem with like, what about like bats? What about like groundhogs that seem to have some sort of consciousness, right? But a lot of what they're doing seems to be explainable by physical properties. So, I mean, is that the type of immateriality that you're talking about?
I think that the type of immateriality I'm talking about with natural forms is mainly the unity of things. Okay. So, and this unity, that seems not to last forever, at least in most natural objects, natural systems. We have the second law of thermodynamics that tell us that the end of the universe, as far as we know, is just the thermal state. But in the case of humans, or at least that we believe, there could be this possibility that we have forms that subsist in themselves, are giving unity to our material body, to our body, but still, because of this evolution of forms in nature, there's a way of getting rid of the body, but still you're immaterial in a superior sense. I don't know whether that answers.
I'm going to take the chairman's prerogative to go back to the point you made about the eschatology, about how some things you cannot really know until the end. And so here we're sitting in the Institute for Quantum Studies. My co-director is Yakir Aronov. And in his view, he has this so-called two-state vector formalism approach to quantum mechanics. And in that point of view, one state vector is not enough. You need two, right? And so if you have two state vectors, this gives you an additional ontology.
Yeah.
Because you can think about pre-preparing an initial state, but then post-lightning a final state. This post-lightning state
You imagine running your precinct, say, forward in time, and you're supposed to say backward in time to make thinking about the present. When you think about this, final state is kind of like a density vector. This takes their role in some sense of eschatology. It forms a complete picture because you know where you're going to go. You may not get that every time, but if you post-select that gives an additional ontological picture, I think, that is echoing some of your things that you're saying in this talk.
I would say so. I was thinking also about the transactional interpretation. I don't know whether it's the same. It's quite similar. Transactional interpretation by Ruth Kastner says that you need to take into account this future state, and then everything, coincides or is coherent. But I mean, the point is that it's impossible for us to predict the future state. But for God, I mean, in a sense, it's a way of saying, yeah, God knows everything because he's present, but creation is characterized by this evolution, and we as human beings cannot ever try to understand the whole picture before it arrives.
Doesn't mean it's not a reality.
Yeah, but it would be a different, level of reality. It's God's reality. Yeah.
One last question. I think at the back we have a question.
Yes, yes, thank you. Thank you so much. Regarding the your course grading and emergence, you mentioned that it is strictly not metaphysical, but can't one retrace this concept of emergent through selection backwards into something more metaphysical, like the properties of laws of nature emerging from other properties? So in that sense, why do you cut it off at the physical only
level?
No. I'm trying to extend this explanatory logic to all levels, so atoms, molecules, cells, organisms. So I think this is working from the Big Bang or whatever it is.
But prior to that, no?
Well, prior to that, maybe there's a selection of the universe. Yeah, maybe, who knows? But as I understand, selection is always the role of formal causation. Formal causation goes with selection of something. And for me, selection of something is always selection of efficient causation, not of matter. But that's another interpretation of hylomorphism that I'm deriving, and I'm working on it. But you have always this enormous set of possibilities for the physical interaction. And what we know is the universe is not ergodic. So it's very, very,
Thank you.
Okay, I'm not doing a very good job as chairman because I'm
Sorry.
in this discussion. So here's what I'm going to propose. We're going to go take a conference photo now into our scientists. We're going to come to take a photograph, take a coffee break, and we'll start again at 3 o'clock.
Yeah, so you speak about the evolution of
Welcome back, everyone. I'm happy to introduce the last session of the day. So our first speaker is Father Thomas Davenport, American physicist and philosopher. We're joining the Dominican Order of St. Physics, the California Institute of Technology. We're going on to earn his doctorate of physics from Stanford. So his research was writing and testing simulations for high-energy particle colliders like the LHC. After joining the Dominicans, he studied philosophy and theology in preparation for his ordination in 2017. In addition, he learned a licentiate in philosophy from the Catholic University of America, philosophy of science and natural philosophy. In 2020, he joined the faculty of philosophy at the Pontifical University of St. Thomas Aquinas in Rome, where he teaches philosophy of nature and epistemology, while working on a second PhD in philosophy. He's a frequent speaker of topics related to the intersection of faith and science, and contributor to a number of projects, including the Thomistic Evolution Project, Science 101, and the annual Thomistic Philosophy and Natural Science Symposium, hosted by the Thomistic Institute in Washington, D.C., and he serves also on the board of director for the Society of Catholic Scientists.
Very good. Very much. It's a pleasure to be here, and I want to thank Vincenzo and Andrew and everyone who's been organizing it. And I do apologize. I'm going to have to miss tomorrow morning because that last thing he mentioned, the annual Thomistic Conference on Philosophy and Science, starts tomorrow afternoon, and I need to be there because I'm organizing it. So, but it's a great pleasure to be here. I kind of hemmed and hawed about whether to how much to adjust this talk at various points because of this conference. Because this talk was originally aimed primarily at a kind of Thomistic audience, and I'll say a bit more about that about trying to encourage Thomists to think more deeply about contemporary science, but in a particular mode. But I have a few brief prefaces, so I decided not to sort of fundamentally change things, but to add a few brief prefaces to try and sort of contextualize this for this audience and the conference we've been in. So this is an exercise or research proposal in the philosophy of nature. So this is not a done project yet, but this is an attempt to push Thomists to work harder in philosophy of nature in a particular way. And the way I understand philosophy of nature, it includes philosophy of physics. I do hope that this would at some point touch with the kind of Thomist approaches to quantum mechanics of hylomorphism and other questions more directly. But at this point, I'm intentionally not doing that yet. Sidebar, I kind of think physics is part of philosophy of nature too. That's a whole internal Thomist debate about things. If you feel free to ask me later. This was not intentionally a follow-up to Father Verrill's talk. It kind of is, although I'm approaching it. I don't really care about sensation today. I'm just thinking about what is the physical stuff that is light. And again, this is complementary to the kind of good work being done by various Thomists trying to interpret quantum mechanics. But Father Little presented, Dr. Simpson, other work by Dr. Pruss, Kuhns, others. But I'm intentionally being agnostic about the details about that for now, because I think there are things we have learned from quantum mechanics that don't fundamentally depend upon our interpretation of quantum mechanics that Thomists haven't learned to handle well, or haven't tried to handle well. And I think I want to sort of present what that might look like, coming in a weird way from both the very, very bottom and the top. So I'll say more about that in a minute. In that context, I'm just going to presume hylomorphism is true. Sorry. I'm going to take it for granted that there's at least a way in which we could complete something like this project. I don't want to therefore say, but I want to say that I want to be deeply respectful of quantum mechanics, that the mathematics and formalism of quantum mechanics, as we have experimentally confirmed them, are very true, and I'll be using some of those details. I'm open to the fact that there might be something incomplete about the formalism as understood, perhaps something like Dr. Simpson's proposal of adding, and I find something like that compelling, the idea that there might be some sort of local constraints that adjust the kind of universality of the wave function in some way. So I'm intentionally going to be a bit vague about those details. If you want to push me on it, William has been trying for a decade to get me to actually say what I think about quantum mechanics. I've been avoiding it till now, or what interpretation of quantum mechanics I prefer, and I've been sort of still on the fence. And again, there are a few lessons I think that I would like to say are independent of the specific Thomistic commitments, and about the idea that we need to learn to have an interscientific disciplinary approach to these philosophical questions. Sometimes, again, it's as difficult to get any scientist to talk to any philosopher, but it's also really difficult to get some scientists to talk to even their neighbors. I'll use myself as the example. I mean, I can count on one hand the number of serious conversations I had with grad students or professors in theoretical condensed matter physics when I was a grad student at Stanford. I talked about sports and football and other stuff all the time, but I don't remember getting into now that might be a me thing. But I think there's a sense I have learned much more, through different kinds of interdisciplinary work, how valuable it is to get out of my own scientific bubble, and that leads to insights that you might not have thought of. And so kind of talking to your neighbor just above you and below you can kind of give some context in some ways. And I'll try to model that a little bit. Okay, so that's my already too long brief preface. I begin this with a quote from Richard Feynman. I think he's just a great kind of explainer of physics in many, many ways. And he has this quote from Volume 2, Chapter 31. I picked the quote because I like the quote, but it's also kind of nice because it comes from the beginning of the chapter where he's starting to explain refraction and how light moves through matter. He says, physicists always have a habit of taking the simplest example of any phenomenon and calling it physics, leaving the more complicated examples to become concerns of other fields, say of applied math, electrical engineering, chemistry, or crystallography. Even solid state physics is only about half physics, he says, which, oh man, I guess some friends be bad at that, because it worries too much about special substances. For instance, one of the most important properties of crystals or of most substances is that their electric polarizability is different in different directions. But in physics, we usually start out by talking about the special case in which polarizability is the same in all directions to make life easier. We leave it out of the case into some other field. So that's a quote from Richard Feynman. This is a quote from me. Thomists always have a habit of taking the simplest example in any phenomenon and calling it natural philosophy, leaving the more complicated examples to the concern of some other field. So in some ways, my primary motivation for this is just recognizing my own lack in like getting asked questions. Well, what do Thomists think about blank and not knowing what the answer is? Or asking other Thomists, what do you think about blank and not knowing what the answer is? Thomists are very concerned, as you have already seen today, with the idea of hylomorphism, the confidence we have in substances and how important substances are. And depending on the kind of Thomist you talk to, they can get into very, very deep conversations about the nature of the substance that is the separated soul that none of us have ever experienced, that thankfully have never experienced yet. But they would have a really, really hard time telling you how many substances are sitting on the surface of this table. And that's what I want to push back against, of like, how do we build up intuitions about how to use this hylomorphism in deep context? And so I'm going to bring some, this is my approach to this. So I don't want to claim this is all Thomists would agree with this. And in fact, there are probably lots of things that Thomists might push back on. But I want to try to motivate what we might try to say about light in particular, and particularly light as it, I will argue, interacts with and really exists in inanimate substances. The substances Thomists are most confident in is the human person, and then after that, animals, and then they talk about plants, but they don't really know how plants work. I am fairly convinced, and I want it to be true, that in this bottle is one substance of water. And there is light passing through this one substance of water, doing weird things. So it gets like a little bit of a shadow. You can't quite see the weird squigglies. I'm not sure if that's the plastic or the water. I want that to be the case. And I think there are other Thomists who would agree for various reasons, drawing on things from thermodynamics and quantum chemistry. I'm going to sort of take that as a starting point, that there are inanimate substances in the world, and ask, what's going on with the fact that light is going through here? And what does that teach us about what a Thomist should think about what light is? In short, this is again, unintentionally an answer to Vincenzo's question about photons. Are photons a substance? My short answer is, I don't think photons, the vast majority of photons that have existed or do exist have ever been substances. I can imagine a few very, very strange cases where you might have a substance that could be composed of just photons or a photon, but I think that would be that's a very rare situation. Most photons, I think, are in fact part of other substances, and I'll try to explain that. Okay. This is a more legitimate philosophical authority to reference this, that even if you don't take my word for it, Ludwig Wittgenstein has this quote about the main cause of philosophical disease is a one-sided diet. One nourishes one's thinking with only one kind of example. I think this comes out even in the sciences too, where it's like we get our pet theory. I mean, my joke is like, I was a theoretical particle physicist. It's like, oh my gosh, theoretical particle physics, that's great. Yeah, so my technical expertise, like if I had to sit on the chalkboard, not anymore, and try and actually solve problems, I was technically trained and competent to deal with up to maybe 6 electrons at a time, maybe 8 on a good day. With a computer, I could do more, but and that was powerful in its own right. but like it colors the way you think about things. Okay, so I'm going to try to go through this relatively quickly. I want to say a little bit about light from the perspective of a particle physicist. Then I want to say some things about what Aquinas got wrong and what we can learn from that. And then I want to say a few things that individual scientists might get wrong. Namely, this is stuff I got wrong until I kind of thought about it more deeply, and I think might be the case for others. And then chapter 4 is there's a lot of slides there with a lot of text that I'm probably not going to go into details of. If somebody wants to get into the super deep Thomist weeds about it, I've got thoughts, but I'm going to try to at least motivate where I'm headed with this by the end, in a reasonable time. So why is light different for a particle physicist? Now, this is a hugely, I mean, in one sense, this is hugely important, right? Because on the mechanist view that the early moderns have, like if light was just a particle, it didn't have properties. So light was just one among many. Like the only difference would be maybe its shape or its size. We don't think that way. Light is, there we go. It's one of the particles of the Standard Model. Photons are one of the particles of the Standard Model. So this perhaps you're familiar with this. So you have the quarks that make up protons and neutrons and hadrons. You have the leptons, the familiar electron, the less familiar neutrinos and muons and tau. You have the photon, gluons, boson, the W and Z boson, the Higgs boson. How many of these do we ever actually interact with directly? First off, like almost never these. Like kind of these, but not really, only clumped together. And even the electron is sort of like usually only ever engaging it in some kind of bound state. Photons stand out as weird, as in the fact that they're like a fundamental particle that just sort of, it's the stuff in the room I can point to in a direct way that actually manifests itself in some sense. What gives? Again, there's a little zoom in. So the numbers here, right? All sorts of fancy numbers. The numbers here are quite simple. There's no mass. There's no charge. There's no charge. And there's a singular spin 1. So photons have no conserved internal quantum numbers. Charge, color, lepton number. They can interact with anything that has charge. There's no other limitation on them. Other things might interact with charged things, but only under certain circumstances, or might only interact with things that have a particular color charge. As long as the energy, momentum, and angular momentum are conserved, along with the charge, like they'll interact with any charged particle. They have no mass. They are fundamentally stable. There's no the decay lifetime for a photon. They never are at rest in any frame of reference. They are never at mutual rest with respect to any massive particle. Every massive particle can be placed in a rest frame. When it's in that rest frame, light is moving at the speed of light. So they are just acting fundamentally different than most of the other particles we're talking about in the Standard Model. They have no stable bound state with any other particles, even themselves. Again, there's some artificial ways in which we can stabilize them, but in nature, you don't find atoms of electrons sitting around. Atoms of photons sitting around. Photons transmit energy at the speed of light, and they kind of come in, they're created, they hit things, they interact with things, and then they go away. But they don't sort of sit in stable states, and you can't get a hold of them in the same way. They're spin 1. There's no Pauli exclusion principle. You can cram them together way more than you can any fermions. That's why lasers work. You can just keep cramming more and more photons in the same energy states, but you can't do that with electrons, with quarks. So there's just sort of something just as a particle physicist kind of interesting about it. And that's at least in part why it is that light is of the fundamental particles, is so accessible to us. In sum, photons are really easy to produce and destroy, and an easy way to add or remove energy from any charged particle. And so they interact with almost any kind of system that has any kind of charged stuff in it. And so they're just that, again, it's sort of we take that for granted as physicists, perhaps. I mean, I know I kind of did, but it's like it is weird that this is the only fundamental particle we just sort of engage with on a day-to-day basis directly. There's something kind of weird about that. Again, there's some caveats there. Okay, so that's some things to keep in the back of the mind from the physics side, or from the particle physics side. So I want to say a little bit about things Aquinas got wrong. I'm kind of jumping off of a little bit from what Father Robert Verrill presented. Aquinas was completely convinced that light is not a substance or a body. It's not like a piece of earth. It's not like a piece of water. It's a different kind of thing. It is an active quality that follows from the substantial form of a body, which is itself luminous. So light doesn't ever exist on its own. It only exists in relation to bodily substances. And it exists to bodily substances roughly in one of three ways. So physical bodies that are not light have one of three relations to light. Looks, they're luminous. They are a source of light, the sort of thing that has the active power to produce light in something else. They are diaphana or transparent. They have a passive quality to be receptive of light from a luminous body, but they are not themselves the source of that light. Or they're opaque, opaca. They have the inability to produce light or be receptive of light, often having some sort of surface that is either mirrored or colored. So light will interact with the surface, but won't interact with the body, full stop. That's nice. Every physical body is luminous, transparent, and opaque, depending on the wavelength, frequency, energy, polarization of the light photons in question. Every physical body gives off thermal radiation. Every one of you is giving off photons right now. We are giving off at least some kind of infrared radiation that can be picked up by a thermal camera. So every body is giving off light. Every body is luminous. And every body is more or less transparent to different kinds of light, depending on what light we're talking about. The things that we just sort of think of as transparent because they're transparent light are opaque to other things. The atmosphere itself is transparent to visible light and radio waves, but mostly, thankfully, opaque to ultraviolet light and many other wavelengths. We ourselves are fundamentally opaque I am opaque to visible light, but X-rays work. And there is a kind of light that will pass right through parts of my body, but not others. So we are all, in some sense, transparent, in some sense opaque, depending on the kind of light we're talking about. What determines which wavelength something is more or less transparent to is something about the chemical constitution of the body, which I'm going to kind of briefly summarize is sort of like how the electrons are arranged, the electron structure of what electrons what transitions are possible for these electrons in the particular atomic, molecular, and chemical structure they have. Again, at high energy, the scattering cross-section for certain things gets more flat. As you get down to lower energy, where like most photons will just break things, as you get down to lower energy, you get more interesting spectra of what's opaque or not. But depending on the photon, that whether or not how it interacts with the matter it's moving through depends deeply on the structure of that matter. So the absorption spectrum for liquid water looks something like this. For a diamond, looks something like that. And so this leads into, okay, well, what happens when light photons enter a transparent body, right? So there's, again, the kind of classical physics explanation. If you're wanting to nerd out on something for a while, there's a great 4-part series on this by this math YouTuber, 3 Blue 1 Brown. Here's just like, he does amazing animation stuff. Oh, sorry. Oh man, okay. But he does a whole series. It's actually based off of Feynman's description of diffraction passing through things. He's talking about that, like visualizing the classical story of the oscillation of charged particles as they are reacting to a plane wave of a light passing through, and how that affects the plane wave as it goes. The point I want to make is, oh no, not that was wrong to the push. Sorry. The point I want to make is that this is not the story about, even in the classical picture, of what happens to light when it passes through matter is a deeply like collective thing about the details of how many electrons there are and how they're arranged. Okay, let me share screen again. Nope, no, I need to do this first. Sorry about that. And this, awesome, share, boom. All right. Nope, okay. In quantum electrodynamics, it's even weirder. Again, this is from Feynman's book, QED, sort of really great kind of general audience introduction to quantum electrodynamics. And he's trying to explain how quantum mechanics, quantum electrodynamics, quantum field theory understands how photons interact with matter. And it's weird. The way the mathematics is best understood is to say that you consider every single possible path the photon takes and work out the interference pattern. It's the double slit on steroids. You take the double slit and just apply it across all of space. Again, that's one way to visualize it. It's not perfect. People can debate that. But the point I want to make is that, again, what happens to an individual photon is not only probabilistic, but those probabilities depend deeply on the physical structure of exactly how the atoms and electrons are arranged. Like, what makes a beam splitter is deeply dependent upon the chemical structure of the glass and silver or whatever kind of crystal you're using to make a beam splitter. So how do we understand, like, how do we get to the macroscopic pattern of saying, well, 50% are going through, 50% are not? If you talk to, we quantify the way light tends to pass through a particular kind of body by a complex index of refraction. And the value of the index of refraction is deeply dependent on how the electrons and nuclei are arranged and free to move. But working out in detail of those relations and its effects on the index of refraction is very difficult to do in detail. And my understanding, again, from talking to condensed matter physicists and quantum chemists, not something we can necessarily do a priori from first principles. Generally speaking, we approach these things by various numerical methods, generally involving positing relatively fixed nuclei and then a kind of field of electrons, and then working out the Coulombic attraction, the electromagnetic attraction between the unfixed electrons and the relatively fixed nuclei, and we work out a kind of approximate solution to the Schrodinger equation. That's our best understanding of figuring out that index of reflection. Generally speaking, the electrons in these complex systems are, at least, and here I'm a little bit fuzzy hand wavy, like entangled and indistinguishable in important ways, insofar as they are bound to particular atoms or in some sort of molecular structure. And we can't properly talk about, okay, well, this photon interacts with that electron or it does this. Like, even if we talk about individual photon, it's interacting with a whole host of electrons all at once in some sense. At least that's the best way to understand the mathematics. Again, I'm going to sort of leave it a little bit hand wavy there. The thing I want to push is like, well, okay, great. Well, what's the Coulombic attraction? What's this force between the electron and the nucleon we've been talking about? Well, if you ask Feynman, it's more photons. The Coulombic attraction is an electromagnetic attraction in the vision of quantum field theory is a kind of photon interaction. Now, these are virtual photons for the most part, which means that they violate, like mathematically violates, are off mass shell. So you would not, it gets weird. They violate mass shell. It's sort of like these things might, technically speaking, kind of have a mass, even though photons never have mass, which sounds really weird. And then you get like weird things where you get a photon and a random electron pops in and more photons. But as far as I know, and Steve, correct me, no one ever does this calculation in terms of trying to solve the Bohr model of the atom using quantum field theory from first principles. But that's our understanding of what's going on at the level of quantum field theory. And again, why the heck would you think that you need so many photons? What's the point? We've talked, it's been mentioned a few times about like quantum mechanics being the most accurate theory. Now, now this is different than the claim about the most tested theory, not most tested most often, but the theory for which the prediction and the experiment are closest is in quantum mechanics, yes, but technically in quantum field theory, it's the anomalous magnetic dipole moment. I'm going to skip over the details because I can't remember them. Sorry, I'm a theorist. The point I want to make is like, at the first order theory, right? So this is basically if this is an electron and a photon coming off of it, the first order Feynman diagram, the answer to the answer to the thing we're trying to measure is 0, and that doesn't quite work. That's not where the actually comes from. The actually comes from adding more than first order terms. So you add a term like, oh, maybe, yeah, we only like, again, what does it mean to see the photon? Like maybe, yeah, there's only one photon emitted, but maybe there's this weird photon that just sort of like is messing around in there for a while and then goes away. a virtual photon that's there for a bit. So, okay, that's better. We're like, okay, yeah, we're down to like 4 degrees, 4 significant figures. That's getting good. How do we get to the stated 10 significant figures? That's second order. Second order, 4th, 6th, 18th order. This is sort of like a sketch of the 12,672 possible 10th order terms that you calculate and incorporate into the theory to get you this thing. So notice like there's tons and tons of photons as well as weird electrons popping in here and there. The point I want to make is this idea of virtual photons as having some kind of physical effect. Ontologically, what are we saying there? There's big questions there. But there's a kind of photon-like activity going on in relatively simple material systems. And we, in some cases, can test this very accurately. And we think it's going on anytime there's electromagnetic interaction between things. That there's at least some sense of a kind of like virtual photonic activity going on. So in a certain sense then, going back to, well, what is this Coulomb attraction that that condensed matter physicists are using when they are talking about and figuring out the index refraction of light? They are, at least in a certain sense, it can be understood, they are talking about a kind of photonic activity, of kind of virtual photon activity going on in the midst of these crystals. That the reason light interacts with this crystal in this way versus that crystal in that way is because of what light is already doing, other light, like light of some kind, photon activity of some kind, is doing in those complex chemical systems. So the intuition then, this is sort of this is the end of the physics portion of the talk, and it's mostly just to kind of like reminding you of things that I had forgotten about, and pointing out the way in which even physicists tend to forget these sorts of things, where the condensed matter physicist doesn't think that often about virtual photons, and the particle physicist might think about them too much. But when we talk about, say, a photon passing through a beam splitter, we can't, mathematically, we might be able to isolate the system. And so I agree the idea that under certain circumstances, it might not matter what the experimental design is, and often doesn't, and that's great. But physically speaking, in terms of what actually is there is a substance that photon is passing through and is doing something different before it enters that beam splitter than when it's in the beam splitter, than when it's out of the beam splitter in whichever direction it's going. So this is where the intuition that I think Atoma should have, that there's at least something of what Aquinas has to say that's not unreasonable. That electromagnetic radiation, photons, are a kind of quality, in the third piece of qualities, the technical thing, that inhere in various kinds of bodily substances. Not just various kinds, all kinds. All bodies are sources of light, opaque and transparent. All bodies interact with light and are constituted, at least in some weak sense, by some kind of photonic activity insofar as electromagnetic attraction binds together all of chemistry. So for the sake of time, because I feel like I'm answering questions that people aren't actually going to ask, there are pieces and parts of what Aquinas has to say that I think are helpful here, but need great development. This is the point where most Thomists would say, oh, well, then maybe the photons are virtually present. And that might be the right language to use, but we as Thomists need to really step up our game about what that language means. To jump ahead, here is a kind of like sketched out vision of what I think is going on in, say, the diamond on the front slide, about how you would think about how to think about, if we want to talk about the diamond as a substance, how do we take seriously what's going on with all of the parts of that substance? Because for various reasons, the Thomists aren't going to want to say, they're going to want to say something different about different kinds of parts, in the same way that, properly speaking, I can talk about my heart, but there's something different about my heart existing in me and not existing in me, that what my heart is only really fully makes sense in the context of my body as a whole. I can talk about like my power of vision, but that power of vision is mostly the thing that's getting blinded in my eyes right now and having very little to do with my pinky. That powers and activities of animals can be localized and in certain structures, and that we can, while Aquinas doesn't feel the need to do this because he thinks all inanimate things are fundamentally homogeneous, there might be tools for talking about localization of different kinds of activity, maybe along the lines of aspects of particle physics. So the idea, the rough idea is that in a diamond, say, individual substance of diamond, there are parts kind of in the way that there are organs in an animal, but not exactly, because they're, generally speaking, those parts are not sort of stable and in the same place all the time. And the parts, and broadly speaking, even the diamond, while it has parts, those parts are generally much more homogeneous. Diamond is basically the same structure down to the nanoscale, whereas biology gets much more complicated. So the idea is that the relative position organization of various sort of field excitations, whether that's the electron field, quark field, photon field, is relatively homogeneous in this. Parts of the diamond are diamond all the way down. But then we can, like at certain scales, we can notice differences between how those things are organized. The carbon nuclei, broadly speaking, that particular collection of quarks that become protons and neutrons and are arranged are, in a diamond at least, relatively localizable and stable. And for again, not a quantum chemist, but the way quantum chemists talk, they'll talk about them as being like individuated from one another in some sense, insofar as they're not afraid of the atoms and the diamonds swapping places as they might be in other kinds of crystals. Whereas the electrons are also parts, but in a different mode. They're much more diffuse. They're more numerically stable, broadly speaking, although again, there can be sort of virtual electrons now and again. But they cannot be individuated or localized in general. They primarily act as sort of a more general collective activity. And there are, at least in some sense, virtual photons that are not numerically stable in any real sense, but a kind of like photonic activity, a kind of electromagnetic activity that undergirds and holds together this substance. So again, this is a very brief sketch, but I do think there's, in a certain sense, oddly enough, weird coincidences of language. The way that Thomists talk about virtual presence, they can learn a lot from the way that quantum field theorists talk about virtual activity. Because we talk about the photon as being, we distinguish the virtual photon from a real photon. The activity of what's going on is characteristically photonic, but we don't think of the photon as a kind of stable entity that we would expect to engage in a concrete way. I think, so to talk then about, let me skip it, yeah. So then if we're talking about the way the diamond interacts with light, with electromagnetic radiation, there's a kind of material active power, kind of quality of electromagnetic radiation emission in the diamond, insofar as it has some kind of thermal state and has charges that are in fact moving, which is rooted in, again, the relative motion of the parts, again, that we can name, but we want to be careful about not talking about the parts as substances for various reasons. And there can be a fixed number and even kind of fixed relative location to some of those parts, for instance, the nuclei, whereas less so under others. And it's the combination of the relation and activity between these different kinds of parts that give you the particular kind of way that electromagnetic radiation emits from diamonds, if it's just talking about the thermal emission, and a similar kind of thing about a material passive power to transmit, absorb, or reflect electromagnetic radiation, insofar as a particular photon or a whole swath of photon comes in, that substance will react in a way based off of the particular structure it has, the particular way in which it is chemically organized, and which is, again, because at this point, it is hand wavy, but it sort of wants to, the hope would be to kind of map this onto the way that we think about this structure in chemistry, quantum chemistry, condensed matter physics, even down into kind of things going on in the lab. So the idea here is that there's a sense in which we can talk about light, we can name light in the way that I can name, my heart, or like the blood cells that just came out of my heart. And I can name that, and yet we can also say that we don't want to talk about that as being a substance. We can talk about that particular part having a particular kind of activity, or even a particular character of that kind of activity. We can talk about a particular cell in my body that has a particular deformity to it. or even a particular perhaps molecule that has some kind of radiation tag on it. And yet still properly want to talk about that as being a part of a substance, and yet we can still talk about those parts in the context of the way we talk about them in science. I'm going to stop there. There's a lot more. I see. I'm sure there's a lot of steps to fill in this. Some of those steps might be more or less clear to people who have studied Aquinas. Some of those steps might be more or less clear to people who have studied the science. They're vague to me too. But I feel like if this is, I feel like this is a part of the conversation that Thomists need to work on to be able to engage more concretely with the well-established science we already do have. The way that we already know how light and chemistry work at a macroscopic scale, that is based in quantum mechanics, but not completely dependent upon the particular interpretation of quantum mechanics you take out. So thank you very much.
Thank you, Father St. Thomas. We'll be proud of you mentioning again those trigger words of.
Yeah, I warned you that like the last few slides are dense. I apologize.
Good. All right. Why don't we have some questions? Yes, Fernanda.
That was super fun.
Okay, thank you.
I've two, maybe 1.5 questions.
Just two?
Indulge me for a moment and split virtual photons and real photons. And does your argument that there's no substance there hold better for one or the other? And it's 1.5 questions because the next thing I'm going to ask is, if you think about things like radiation pressure, for example, like does this still hold? How do you?
Yeah. So short answer, I guess in a certain sense, it's sort of more obvious that virtual photons are not substances, but I'm careful about, because again, even among Thomists, there's this intuition that like what makes something a substance is being like stable and like around for a while. So I told you, like, I'm pretty sure this is a substance of water. That's a substantial change where I made a bunch of new substances of water. That sounds weird even to Thomists, I'll tell you that. But I want that to be the case. So it's not just about the temporality. So what I think my account is actually that no, there's something about the nature of light itself that it's not the sort of thing that ever exists completely independent of some other physical structure that it's passing through. Even when we're talking about like deep vacuum cases, even if we're talking about like interstellar plasma, I think I still want to give an account of it as a kind of very, 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 very diffuse gas that is a substance through which electromagnetic radiation is passing. And so this is a kind of feature of all physical reality. Like, so there's a sense in which I'm stealing the account of like the universal field of the universal photon field, but saying that's in a certain sense a potential reality, but not an actual reality that undergirds everything. And the way that manifests is different depending upon what kind of substance you're in. Sometimes it manifests in a virtual mode. Sometimes it manifests in a kind of transmissive, more real mode. And the character of both that real mode and that virtual mode are going to depend upon the particular substance and the details of that substance, which would need to be cashed out in detail at some level by some sort of probably something like the interpretation of quantum mechanics that other Thomists are working on.
Just, I agree, Jay. I'd have to do a lot of thinking about your Thomistic approach. But if I remember right, the virtual photons come out of Hermann Weyl's second-order spinners. At least if I use second-order spinners and I take the determinant, I get a massless particle.
Yeah.
But I'm not sure if you're familiar with spinor theory or. Again, you have a single photon as a single vector.
Yeah.
And you have the bifactors would generate the virtual particles.
Right. And so there are different, like, again, in all honesty, I'm rusty on the math and I would need to dig into the math more. But my point is not about, I guess it's in a certain sense, it's less about the details of the particular math, because again, like the virtual photon does not transmit in a stable wave packet in the way that a photon does.
It has to hold together with two things.
Right. So yes, and so that's part of where the second order, fourth order thing. But the point I want to make is that there is a kind of activity that's characteristically photonic that's different than the kind of activity that's characteristically electronic or quarkish, or up quarkish or down quarkish. And so I'm borrowing that notion from quantum field theory and trying to sort of manifest it in a kind of atomistic account.
However, I can transform it to quarks and gluons that behaving like the gluons will analogously be like your virtual photons in that sense.
Yeah, so there would be virtual gluons, virtual electrons. Yes, there could be those sorts of things.
Only virtual, if I've ever seen it.
Father in the back.
Thank you. Following you, what is a wave? Is a third a quality?
So I would say, let me think about this. A wave in general. I think I want to depend on the exact wave I'm talking about. So when I imagine the photon, when I imagine a photon as a wave packet, either like the single photons that Vincenzo's talking about, or just the kind of like massive amount of photons that form a kind of plane wave here, I want to say that those are qualities existing and passing through a substance, activating a passive quality of the transparent substance, insofar as the substance is in fact transparent to that kind of photon.
Could it be applied to any particular?
So I don't know. I don't know if I would want to say exactly the same thing about like a water wave. Do I want to talk about a water wave as a kind of quality of water in the same way that a photon wave is a quality of transparent mediums? I'm not sure I want to go there. So I don't want to say I'm giving like a universal definition of how all waves work, but I think insofar as we think about what like particle wave, insofar as we think about fields in quantum mechanics, to be super Thomist about this, they're kind of actually just Aristotle's elements. But only that they only ever exist in they only ever individually exist in potency to kind of combined states. So they are ways in which matter can manifest with some particular interior properties, namely the spin, mass, charge. So that's why I want to say something different for the waves of the standard model and water waves. I don't want to give that kind of interior properties to water waves in the same way.
Okay. It seems to me that substance is kind of a analogous term. That when Aristotle or Aquinas think
you're scratching a good Thomistic itch here. Everything's analogous. No.
But the practical Aristotle or Aquinas is an organism.
Yeah.
Maybe it's an artifact. But when we think about a rock, planet, solar system, and a galaxy, we consider each of those substances of which we can, predicate accidents and so on. But some are parts of others. So there's not like one level of substance we get out of the biological and artifact realm.
So I would, some distinctions there. There's absolutely a hierarchy in substances, but that doesn't mean that doesn't mean that the lowest parts aren't substances. So, Aquinas, again, I can go to the 13th century and tell you what Aquinas thinks directly, that he's absolutely clear that like rocks and minerals are substances. I want that to be true. Again, a lot of work to do. But I want that to be true for various reasons that I think are reasonable. They are going to necessarily be much less active and in some ways much less interesting than biological substances. But my push on this is most Thomists only think about substances in the context of animals. Like when they think of substantial form, what they're actually thinking about is animal soul. And animal soul does way more than water does or diamonds do. And so you get a bad notion of what a substantial form is if you focus too much on the biological. Those are substantial forms, but they have more to it because they are substantial forms of living things. So this is my calling out to Thomists to think about rocks and in the inanimate world a bit more.
But Thomists tend to deny that there can be a hierarchy of internested forms.
They're not internested. So any
rocks make planets and planets make solar systems.
Oh, okay. Sorry, you're going that direction. Okay. I don't think of planets as a substance. I'm open to the possibility that maybe a star is a substance, but I have to think about that. I think this is work Thomists need to do, because if you ask Thomists how many substances are filling the space between you and me, they couldn't tell you.
How do you begin to
No, exactly. No, exactly. So we need to build better intuitions on this, drawing on Aquinas, but also engaging with contemporary science. I have thoughts on like gases and plasmas and how to think about that. Like I think a plasma is probably a collection of substances interacting in a certain way, but I'm not 100% sure. Kind of go back and forth on that. Rocks, I'm a bit more confident in just because of the nature of their stability. But yeah.
I think we're out of time. Thank you, Thomas. Again.
Bring up Professor Barr's.
Oh,
Right, so this will change before that does, but the earpiece should work. Okay, and then the microphone?
Yeah, I will help.
Thanks.
Put that in pocket somewhere.
All right. Okay, so the last talk of the day is Dr. Stephen Barr. He's retired professor of theoretical physics from the University of Delaware and the founding president of the Society of Catholic Scientists. He has the undergraduate degree from Columbia University and the PhD in physics from Princeton University. He has a great interest in the philosophical implications of quantum mechanics and is looking forward to spreading his ideas on the subject at this conference. He and his wife have been married for 44 years, have 5 adult children and 6 grandchildren. So welcome, Dr. Barr.
Thank you. Hear me okay? Good. I want to warn you, I have this thing called myasthenia gravis, and late in the day, I sometimes start slurring my speech. So I just want to say I'm not drunk, in spite of the intoxicating talks that we have heard up to this point. Okay, so physicalism, physicalism is the claim that everything is ultimately reducible to physics, including human minds and thoughts. In the view of some, however, quantum mechanics implies that there is more to the world, and in particular to minds, than the equations of physics can describe. The argument has a long and distinguished pedigree. It goes back at least to John von Neumann's classic book, The Mathematical Foundations of Quantum Mechanics in the 1930s, and to the physicists Fritz London and Edmund Bauer. In the latter part of the 20th century, it has been defended by such eminent physicists as Sir Rudolf Peierls and the Nobel laureate Eugene Wigner. Physicists who have written books defending it more recently include Henry Sapp of UC Berkeley and, I don't know how you pronounce his name, I'll say Evan Squires of the University of Durham in the UK. Peierls, for example, said the premise that you can describe in an interview, he said, the premise that you can describe in terms of physics, the whole function of a human being, including its knowledge and its consciousness, is untenable. There is still something missing. He's basing that on quantum mechanics. Wigner stated flatly in a famous essay written around 1960 that while solipsism might be consistent with quantum mechanics, materialism is not. Now, the starting point of the anti-physicalist argument is the crucial fact that quantum mechanics is inherently probabilistic, as we've already heard. Roughly speaking, in classical physics, one calculated what actually happens, whereas in quantum mechanics, one calculates the relative probabilities of various things happening. A familiar example is the idea of the half-life of radioactive nucleus. Suppose a certain type of nucleus has a half-life of 1 hour. That means that a nucleus of that type has a 50% chance of disintegrating or decaying within an hour, a 75% chance within 2 hours, and so forth. And so on. The quantum mechanical equations do not and cannot tell you when a particular nucleus is going to decay, but only the probability of it doing so within any given period of time. In quantum mechanics, probabilities are encoded in wave functions. Wave functions and the probabilities they encode evolve in time according to an equation called the Schrödinger equation, as we've already heard many times. Now we've arrived at the crux of the matter. We're talking about probabilities of events, events such as a nucleus decaying or a particle entering a detector or something like that. Yet there's something paradoxical about the very notion of the probability of an event. It does not make sense to talk about the probability of an event unless at some point it stops being a matter of probability and becomes a matter of definite fact. For example, suppose I say that Jane has a 70% chance of passing the French exam. That only means something if at some point Jane will take the French exam and get a definite grade, either passing or failing. At that point, the probability of her passing no longer remains 70%, but suddenly jumps to 100% if she passes and 0% if she fails. But if she never definitely passes or definitely fails, ever, then this probability of 70% meant nothing in the first place. In other words, probabilities of events that lie in between 0 and 100% must at some point jump to 0 or 100%, or else they meant nothing in the first place. This raises a very thorny issue for quantum mechanics. The Schrödinger equation, which governs how things evolve with time, does not yield probabilities that suddenly jump to 0% or 100%, but rather probabilities, generally speaking, it gives you probabilities that vary smoothly with time and that generally remain in between 0 and 100%. Radioactive nuclei are a good example. The Schrödinger equation says that the survival probability of a nucleus, that is the probability of its not having decayed, starts off at 100% and then falls continuously and monotonically. In fact, it falls exponentially, reaching 50% after one half-life, 25% after two half-lives, and so on, but never reaches 0. No matter how many times one divides by 2, one never reaches 0. In other words, the Schrödinger equation only gives probabilities of decaying, but never an actual decay. If there were an actual decay, the survival probability should jump to 0 at that point. To recapitulate the key points, first, the equations in quantum mechanics yield probabilities. That's what the equations do. Second, to mean anything, those probabilities must be the probabilities of definite events that happen or do not happen. Third, when definite events happen, some probabilities should jump to 0 or 100%. However, and fourth, the equations of quantum mechanics do not describe such jumps. One begins to see how one might reach the conclusion that not everything that happens is describable by the Schrödinger equation. So how do minds enter the discussion? So that's basically the anti-physicalist argument. Something is going on, especially when a measurement is made and you say, the nucleus decayed. Something has gone on that the Schrödinger equation is not telling you. Now, how do minds enter the discussion? The traditional understanding is the so-called Copenhagen interpretation is that the definite events that happen or do not happen, and whose probabilities one is calculating, are the outcomes of measurements or observations. If someone, traditionally called the observer, checks to see whether, say, a nucleus has or has not decayed, perhaps using a Geiger counter, he or she must and will get a definite answer. When the observer comes to know that answer, his or her knowledge suddenly changes. At that point, the observer has to set the survival probability of the nucleus to either 0 or 100%, depending on what he or she has learned from the measurement. This sudden change in probabilities must, of course, be reflected in the wave function that encodes those probabilities. The wave function must suddenly change. This is called traditionally the collapse of the wave function. Schematically, the wave function of a radioactive nucleus looks as follows at the top, as long as no measurement is made. The wave function has, there's two coefficients in that top equation. One, alpha of t, is, and the other is beta of t. Alpha of t is called the amplitude that the nucleus has decayed, and beta would be the amplitude that it has not decayed, and these are time dependent. And when no measurement is made, these coefficients evolve in time according to the in a way told to you by the Schrodinger equation. But if I make a measurement at time capital T to see whether the nucleus has decayed by that point or is still there, the probability that I will find that it has decayed is given by the absolute square of alpha of capital T. And the probability what is not decayed is the absolute square of the beta of capital T. This prescription for extracting probabilities from the wave function is called the Born rule, as we've heard a number of times, after Max Born, who proposed it in 1926. An important point to note is that neither wave functions nor the amplitudes in them are themselves probabilities. They could not be, since their values are in general complex numbers. Rather, they encode probabilities in a way given by the Born rule. Okay, now what does the wave function of the nucleus look like right after the measurement? Well, it depends on what the outcome of the measurement was. If the measurement showed that the nucleus decayed, then right after the measurement, the wave function looks like, well, the first red equation at the bottom, or if it has not decayed, it looks like the second red equation. In other words, one throws away or cuts off the part or parts of the wave function that describe outcomes that are known not to have happened, and retains only the part corresponding to the outcome that is known to have happened, resetting the coefficients or amplitudes to be complex numbers of magnitude 1, because now the probability is known to be 100%. Now, many physicists find the idea of the collapse of the wave function, this throwing away of parts of the wave function, strange, to say the least. It goes against the intuition that physical processes should unfold in a gradual and continuous way, as described by the equations of classical physics and also by the Schrodinger equation. As I've mentioned, however, the discontinuous collapse of the wave function that occurs as the result of a measurement simply reflects the sudden change in the observer's knowledge. Probabilities of events, one can say, refer to someone's state of knowledge. For example, before I knew the outcome of Jane's exam, I could only say that she had a 70% chance of passing, whereas after I know, I must say either 0 or 100%. Since wave functions encode probabilities, they encode someone's state of knowledge. When that observer's knowledge changes, as it does suddenly at the end of the measurement, the wave function must change suddenly to reflect this. To quote Sir Rudolph Parles again, the moment at which you can throw away one possibility and keep only the other, that is, throw away parts of the wave function, is when you finally become conscious of the fact that the measurement has given one result. You see, the quantum mechanical description is in terms of knowledge, and knowledge requires somebody who knows. By the way, he emphasized somebody, and we'll get back to that in a minute. Heisenberg himself wrote, the discontinuous change in the probability function, which he means the wave function, takes place with the act of registration of the result of the measurement, because it is the discontinuous change of our knowledge in the instant of registration that has its image in the discontinuous change in the probability function. So they're basically saying what I just said before. Oops. The intuition that physical processes should unfold in a continuous manner is not necessarily wrong, but the collapse of the wave function is reflecting a change in knowledge, and that is not necessarily just a physical change, unless one is a physicalist, in which case it necessarily is a physical change. Indeed, the point of the anti-physicalist argument I've been sketching is precisely that it is not. An obvious question is why one would need to talk about knowledge and minds at all. Could not a physical device that totally lacked consciousness, say a Geiger counter, be the observer and carry out a measurement? According to von Neumann, Peierls, and others, the answer is no. That's why Peierls, who was asked exactly this question in the same interview, answered that the collapse of the wave function required the observation of, quote, somebody who knows, not something. The reason is the following. Suppose the observer were just a purely physical entity, such as a Geiger counter. Then one could, in principle, write down a bigger, more inclusive wave function that described not only the thing being observed, say a radioactive nucleus, but also that purely physical observer, say the Geiger counter. That bigger, more inclusive wave function would evolve in accordance with the Schrödinger equation. And because of that, the probability amplitudes, as we have seen, would not collapse to give probabilities of 0 or 100%. That is a definite outcome, but rather probabilities that remain somewhere in between. In other words, the bigger wave function will have an amplitude, for a non-zero amplitude in general, for the nucleus having decayed and the Geiger counter having registered that decay. And another amplitude, also non-zero generally, for the nucleus not having decayed and the Geiger counter having registered its non-decay. Both those still remain in play, still are amplitudes in the wave function. No collapse occurs to just one of those possibilities. That is the point I made earlier. As long as only purely physical entities are involved, this is so the argument goes, they are described by wave functions that are governed by an equation, the Schrödinger equation, that says that the probabilities do not collapse to a definite result. One remains trapped in a limbo of probabilities rather than the world of definitely observed facts. So you're left with probabilities, not definite observed facts. But here, many people would object that observers, such as human beings, are physical. We have bodies made of atoms. The sensory organs and brains with which we carry out measurements and observations are made of atoms. Therefore, they must be describable by physics. That is all obviously true. Moreover, just as one could include a Geiger counter in a bigger, more inclusive wave function, one should, in principle, be able to include also the observer's sensory organs and brain in an even bigger and even more inclusive wave function. Experimental devices such as Geiger counters are just extensions of our sensory organs, or equivalently, our sensory organs could be considered part of the experimental apparatus, just like the Geiger counter. This leads to a basic question. In quantum mechanics, as traditionally formulated, there was always a system that is measured and that is described by a wave function, and an observer who makes observations, and an observer who makes observations or measurements of the system and that collapse the wave function. The question is where the system ends and the observer begins. Suppose that I am the observer and the system I'm studying is a radioactively unstable nucleus. One could count only the nucleus as the system and consider the Geiger counter, my sensory organs and part of my brain, and the part of my brain that processes the information from my sensory organs, and me in toto as the observer. Alternatively, one could lump the Geiger counter in as part of the system, meaning that there would be a wave function describing both the nucleus and the Geiger counter. Everything else would be considered the observer. Or one can consider not only the nucleus and the Geiger counter, but also my sensory organs as part of the system. And one could move more and more over from the observer side of the line to the system side. So it is somewhat arbitrary where the line between the system and the observer is drawn. That line is sometimes called the Heisenberg cut. Nevertheless, the logic of quantum mechanics requires that that line be drawn. And it must be drawn in such a way that the logic requires that you draw it. And it must be drawn in such a way that there's something on both sides, on each side of the line. If we try to put everything on the system side, you put the whole observer on the system side, which you should be able to do if I'm just a physical entity. Why shouldn't I just have a wave function that's me in toto? Put me on the system side. And then there's nothing left on the observer side, then there's nothing to collapse the wave function. There's no measurement, really. And you end up with a wave function that never collapses and probabilities that never jump to give definite outcomes. To quote Eugene Wigner again, even though the dividing line between the observer whose consciousness is being affected and the observed physical object can be shifted toward the one or the other to a considerable degree, it cannot be eliminated. What is it that must remain on the observer side of the Heisenberg cut? Presumably, it can't be any part of his or her body, for these are physical and should be describable by wave functions. It's hard to escape the conclusion, and this is one that Wigner and Peierls and others have drawn, that it is some aspect of the mind of the observer that is non-physical, that is not describable by the mathematics of your physical theory. Okay, so that is basically the anti-physical argument, anti-physicalist argument. I'm convinced by it, but I'm not insisting that you must be convinced by it. I'm just telling you what it is, okay? The vast majority of physicists would reject this. I think that's largely because of a deeply ingrained materialist prejudice, physicalist prejudice. Even in people who are not avowed physicalists, that physicalist ways of thinking about the world are deeply ingrained even in many people who are not self-professed physicalists. And I think that is why this doesn't get much of a hearing, my own view. But anyway, most physicists would vehemently reject this argument. Now, if one is a physicalist, and assuming that the logic of this argument is valid, what options exist for one if you are a physicalist? Well, there are basically two. Well, first of all, there are many objections have been raised against the traditional understanding of quantum mechanics that I've been describing. Who is the observer? There's the famous Wigner's friend paradox, which I could talk about, but I don't have time. Who qualifies as an observer? As an ant, as a worm, as a frog, as a chimp? Who is an observer? Can an atom be an observer? When does Schrodinger's cat die, and so on and so on. I'm not going to get into all the objections. Now, if one is a physicalist, what are one's options? Well, one, you can do away with observers altogether. You can simply say that the observer, what we call observers, are just physical systems, which means we can lump them all into some wave function of the universe, which encompasses everything, and wave functions never collapse. And that gives you the many worlds interpretation. Okay. I think the many worlds interpretation, actually has serious difficulties. Not everyone agrees. There are many great physicists, there are a number of great physicists alive today, some of the top physicists in the world who are drawn, spouse or drawn to many worlds interpretation. They think it's perfectly consistent. I think it has a problem with the Born rule and justifying the Born rule, but I won't get into that. Now, in the many worlds interpretation, the wave function doesn't collapse, so all possibilities remain always in play. And because we know that some possibilities truly do happen, we see them happen, one seems forced to say that all possibilities that allowed by the laws of physics do happen. but they happen in distinct branches of the wave function that in practice cannot exhibit interference with each other. There are branches where Schrodinger's cat is alive, other equally real branches where it is dead. There are branches where you are listening to this talk, other more pleasant branches where you are lying on a beach somewhere, or watching some soccer or football game. And other branches where you were never born, and so on. All equally real. These branches do not interfere with each other, or to be more accurate, any interference is negligible and indiscernible. So for all practical purposes, they have split off from each other as different worlds, hence the name many worlds interpretation. Most physicists find the idea that every person, and that means you exist in an essentially infinite number of alternative versions, alter egos. Every branch where you are alive, there's a version of you, having thoughts and feelings and so on. So most physicists find that too implausible to accept, but plausibility aside, as I said, there are technical objections many people raise to the many worlds interpretation that I won't discuss, and I'm not an expert on them. The other possibility is to modify the rules of quantum mechanics and to basically abandon real quantum mechanics for some alternative like Bohmian mechanics. I shouldn't have an umlaut over the O, sorry, that was just a typo. Or GRW theory. I have nothing to say about them. I think most physicists think that those are barking up the wrong tree. I think they're ugly. I think they abandon some of the most beautiful aspects of quantum mechanics, and you don't get much in return for it. It's not clear. Well, GRW theory, I guess, could be experimentally distinguished from.
What does GRW stand for?
Something Rontandali. It's three Italians.
Rimini Weber.
Oh, I thought it was right. Okay. Three Italian, three names. I don't remember. That's why the people say GRW. The KWB approximation. Who knows what that is? Of course, so I'm not going to comment on that. But the conclusion of this part of my talk, and how much time do I have left? Well, I'll talk while.
Let's say 15 minutes.
Okay, good. I think I can. The more incendiary and insane, the part of my talk where you will conclude that I am indeed intoxicated is coming in a minute. So the conclusion of this part of the talk, which is is that according to this line of reasoning, which has been found advanced by some formidable physicists, but as I said, like Wigner and Peierls, but is not accepted by most, is that if the formalism of quantum mechanics as we've known it for about 100 years, I said 90, but I'd say 100 years now, and if one is a consistent physicalist, then you're left with only physical systems described by the Schrodinger equation. The wave functions never collapse. And that means you're driven to the many worlds interpretation of quantum mechanics. And that I would simply say is very heavy baggage. Even many people who accept the many worlds interpretation see no alternative to it because they are physicalists and they don't want to screw around with quantum mechanics. And they feel forced to accept many worlds, regarded as kind of nutty and feel uncomfortable about it, okay? But they would say, agree, it's very heavy baggage. And I think that's interesting that physicalism, one effect of quantum mechanics, arguably, is that physicalism now has some very heavy baggage to carry, okay? Now, now let me get to the question of realism. While quantum mechanics creates difficulties for physicalism, many have seen it as creating difficulties for any sensible traditional metaphysics. Some Catholic thinkers, well-known Catholic thinkers, have expressed discomfort with quantum mechanics as traditionally understood, including such figures as the historian Stanley Yockey, the physicist Peter Hodgson, and the philosopher Mortimer Adler. What disturbed them about quantum mechanics is not that it seems to point to the importance of mind or consciousness, but rather that it seems to give too great a role to mind and consciousness. Indeed, they see quantum mechanics as undermining the idea that there is an objective reality that is what it is, no matter what any finite mind knows about it or observes about it. The problem that they have with quantum mechanics arises because the fundamental quantities calculated in quantum mechanics are not straightforward descriptions of the way the physical world is in itself, as was the case in classical physics. As we've seen, the wave functions encode probabilities and therefore seem to refer only to the state of knowledge about the physical world of particular observers or classes of observers. This does not lead to subjectivism in the sense of a multiplicity of irreconcilable viewpoints. Different observers can have different states of knowledge, which change as they make measurements, but these different states of knowledge will all be consistent with each other as long as the observers do not make mistakes. Nevertheless, it is hard to see how one could stitch together all these different observers' states of knowledge into a single unified and complete picture of objective reality, a God's eye view of the world, so to speak. At best, one seems to be left with a patchwork quilt or collage of partial pictures of reality that even together do not give an exhaustive description of the world as it is in itself. Indeed, the collapse of the wave function, whereby one wave function is replaced suddenly by another that differs from it in a discontinuous way, is itself a kind of seam in that patchwork quilt. Now, some people respond to this problem by adopting a purely instrumentalist view of physics. According to this view, physics is nothing except a set of mathematical rules that relate our measurements of the world to each other. But one that does not presume to say anything about reality that goes beyond or lies behind what we measure. This could even be taken in an idealist direction, in which one says that reality consists of nothing but the set of our experiences, and that the laws of physics simply give correlations among those experiences. It could be even taken in a solipsistic direction, as sort of hinted at by or alluded to earlier in that quote by Wigner. So now I will briefly argue that quantum mechanics is need not be inconsistent with a realist metaphysics, in the sense that there is a single objective reality or state of affairs that is independent of what any human being or other finite observer knows about it, and that there can be, in principle, a single, complete, and comprehensive description of the world, though not, of course, one that could be known by any finite mind. And I'm going to make this argument by proposing a kind of, making a modest proposal. This is a hypothesis. I do not propose this as the way things are. I'm increasingly, as time goes on, I'm drawn to believe that it is. I'm just giving it as an example of a picture, hypothesis that I do not think is inconsistent with anything we know. It doesn't force us to modify quantum mechanics. It doesn't contradict anything we know, either in the laboratory or in everyday life. And I call it and it gives you a realist, it allows you to say that there is a single objective reality, a God's eye view of the world. I call it the traveling minds hypothesis. I think it actually it's already been thought of by other people and has another name, but I'm too lazy to track that down. And I don't claim that this is the only way to get a realist understanding of quantum mechanics, nor do I say that it's the best hypothesis for doing that. It's just one that occurs to me. Okay. The traveling mind hypothesis, oops, I skipped a few slides. Quantum mechanics creates a problem for objective reality. Okay. The traveling minds hypothesis supposes that mind or consciousness is a constituent feature of the universe just as real as matter and as fundamental as matter, in the sense of not being reducible to matter. And by the way, I'm talking about consciousness. I'm talking about something that even dogs and cats, I presume, have. I'm not talking about spiritual soul or anything. I'm talking about this natural phenomenon called consciousness, which I regard as a natural phenomenon. And I think the consciousness, mind and consciousness, is mind in the sense of at least, the mind of animals, and consciousness are not reducible to physics, let me put it that way. Now, the traveling minds hypothesis has features in common with both the many worlds and with Copenhagen, though I think it appears to avoid the problematic features of each. Like the many worlds interpretation, it posits a wave function of the entire physical universe that never collapses. The wave function of the physical universe is constantly branching, and no branch gets cut off or thrown away. The crucial assumption of the traveling minds hypothesis is that when such a branching takes place, so that there are now branches which are essentially decohere from each other, all mind and consciousness everywhere in the universe goes down just one branch. Whether it's even if the thing that precipitates the branching happens in this room, all mind throughout the universe, all consciousness, even of some animal on some distant galaxy, all consciousness goes down just one branch. So the picture, unlike the many worlds interpretation, well, it is simply, one does not have to throw away the parts of the wave function corresponding to the outcomes that were observed not to happen. You don't cut those parts of the wave function off. It's simply that those parts of the wave function of the universe describe branches that have no consciousness associated with them. Those outcomes are not observed to occur simply because there is no mind or consciousness within those branches that could experience those outcomes. Now, unlike the many worlds interpretation, I think this allows the Born rule to be applied. The Born rule gives the probability that mind, that is all minds in the universe, will travel down a particular branch. It's not a rule that governs matter, like the Schrodinger equation, but a rule that governs mind. The Born rule does not, okay, so I think the traveling minds hypothesis avoids the two major defects of the many worlds interpretation. First, I think it makes it easier to justify the Born rule, but let's not get into that. Second, it does not posit the existence of an infinite number of versions of every person. You no longer have to believe that there's a version of you in an infinite number of other branches, that there are all these alter egos. You simply refuse to posit their existence. I mean, as things with minds associated with them. So, the other branches of the wave function describe the wave function describe entities that have physical structures that are the same or nearly the same as those of the body of the person or the animal in this branch. Okay, but those structures have no mind associated with them. In the colorful jargon of contemporary philosophy of mind, those entities are philosophical zombies. Now, philosophical zombies are usually discussed by philosophers as logical possibilities that are not natural possibilities. That is, it is not illogical to posit such entities, but it is supposed that they cannot exist in the real world. In the traveling minds picture, such philosophical zombies are indeed not natural possibilities in that single world or branch that is traveled by all mind and consciousness, which is obviously the world that all of us conscious beings inhabit, we inhabit. Every person can therefore be assured that every other person in his or her world, every other person, and also your pet dog, and all have consciousness. We will not encounter a philosophical zombie. Okay? We're in the branch where they don't exist. Okay? Now, the idea that the other unconscious branches of the world have philosophical zombies may be disconcerting, but obviously does not disagree with anything in our experience. How could it? We don't experience those branches. We're not in them. In any case, those branches being devoid of anything that could experience them have only a shadowy existence. So what are those other branches that don't have, so we see the cat dead. Well, there's other branches of wave function corresponding to a live cat. But we say that there's no consciousness in those branches. Are those branches real? Well, you could take a kind of Berkeleyan view and say that they're sort of not as real because, esse est percipi, to be real is to be perceived. There's no one in those branches. There are no beings who experience those branches from within. So you could say they don't exist if you're a Berkeleyan. Or if you're Aristotelian, you might say, well, they have a kind of potential existence. They are things that could have been realized, but weren't. Only the branch with mind in it is the one that's realized. The others were simply potential things that were never realized. It's up to you how you look at it. Anyway, so that is, now it may seem a high price to pay to posit such entities as philosophical zombies in the other branches of the world, but I think Occam's razor cuts it the other way. The laws of physics, the Schrodinger equation, the laws of physics present us with a vast number of branches of the wave function. And most people unconsciously assume, who adopt the many worlds interpretation, just unconsciously, well, no pun intended, they assume that there are copies of us that are equally conscious in all those branches. They posit consciousness in all those other branches. But that is an entirely gratuitous thing to suppose. We're not forced to do that by anything we know from experience, or anything we know from the laws of physics, because the laws of physics, nobody knows how consciousness is what's the right word, supervenes on physical structures. Nobody understands why some physical structures are conscious and others aren't. We don't understand. Many physicists, including many atheists, many philosophers, including many atheists, have said and have gone on record saying consciousness is not something physics can explain. So consciousness is beyond physics, according to many people. And therefore, to deny that certain physical structures in these other branches have consciousness doesn't violate anything we know from physics or anything we know from personal experience. So to posit consciousness in all those infinite number of branches without any real warrant, I think violates Occam's razor. So basically, I'm saying just take many worlds and just refuse to say that all those alter egos of ourselves and of our pet dog and so on have consciousness. They're simply inhabiting these shadowy mathematical possibilities. These other branches have a kind of mathematical existence, and these other philosophical zombies have a kind of mathematical existence, but real red-blooded, full-blooded existence belongs to those who are in the branch corresponding that were to the outcomes of measurements that are actually observed by somebody to happen. And that's where I'll stop. Thank you.
Questions? Let's start with Vincenzo.
No.
Just to clarify, so are you so the consciousness associated to the different states in the superposition, I guess you
but only is only posited of one state in the superposition.
You assign it just to one state of the.
Well, it's there. I don't assign it. Somehow the law, there's a sort of might call a psychophysical law of nature that governs how consciousness.
You have a quantum superposition, and the reason we only one at a given instance on an experiment occurs within the quantum superposition is because in that given instance there was a conscious reality also attached to it.
Yeah, you can also call this a train tracks theory. The wave function is like the train tracks, and consciousness is the train. And when the tracks split, the train goes down one track. That's a little
I understand. So, but in essence, so what we observe as a probability distribution when when we do an experiment where we look at all the possibility for the different amplitude in the superposition is what we observe. So we actually observe that as a probabilistic distribution in the way consciousness itself is attached to the other.
Correct. So the Born rule is a kind of law of nature. It governs consciousness. So people have said that collapse of the wave function is something that happens to the wave function. And I think they say that because they're embarrassed to be talking about observers. Most physicists don't like to talk about minds as if they have any relevance to anything. So they would like to talk about the collapse as something happens to the wave function. I'm saying it's not. It's something that happens to consciousness. It's something that happens to minds. And the Born rule is a rule that governs that. And it says there's a before you do the experiment, there is a 30% chance that you and all other conscious beings are going to be in the branch where the radioactive nucleus decayed, and there's a 70% chance, if I got the number, that it'll be in the branch where it is not decayed. So it's governing the chance that consciousness will go into different branches.
In that sense, the problem of Born rule associated to the actual quantum superposition now is transferred to the probability, the real probability of the conscious observer to be within each of the given branches.
It has a place. The trouble with the many worlds, it seems to me, is you have abolished the observer, and you've abolished observations and measurements as a peculiar kind of physical event. They're just like any other physical event. So there's no special thing in many worlds called an observation, and there's no special thing called an observer, and therefore there's no special point at which you should use the Born rule. And it's hard to justify the Born rule. Here there is. You simply say the Born rule is the index that's making the choice. It's not the wave function collapse. It's which road is traveled by actual conscious observers.
My question is, if there is no observer, so we spoke about a realist understanding of quantum mechanics. If is the way to understand the wave function collapse is to associate probabilistic given conscious observer to any given branch associated to the given quantum superposition. If you take away, and in fact you said that when there is attached to a given branch, when there is no observer to attach to a given branch, it seems that the things not actually even exist.
I mean, how you regard it is up to you.
How do I understand then the actual reality of the states of the particles in the quantum superposition apart from the observer?
In those other branches, all the branches are equally sort of mathematically real. They're all part of a mathematical description of the physics of the inanimate world, shall we say, including our bodies, the molecules in our brains. They're equally a part of the mathematical description. But but the wave function doesn't touch upon. So the God's eye view of the world is the physical level, so to speak, is described by the wave function, the purely physical level. And then there's also a reality, which is mind, which I don't think is reducible to physics. And God knows which way that's going. So God knows everything, and there's a unique state of affairs, and which we may not know, but there was something.
The reality of.
But it's up to you. I mean, what if no observers had ever evolved? Then the many worlds would be, the universe would be as many worlds describes it. All these things would be equally real and equally unreal. There's no one in the universe to experience anything. It's kind of, what if there's a universe and there's nobody home? And what if there's a universe and there's no conscious beings in it? It kind of has a shadowy existence, in my view.
We've got lots of questions in the audience. You were first. Yeah.
Thank you. To say that all minds follow one branch presupposes there is a fact about what the branches are. But in contemporary many world theory, as I understand it, branching is vague. Decoherence gives only an approximate quasi-classical branching, but not an exact unique decomposition. So it seems to me that you need something else in your ontology to determine what a what counts as a branch.
Yes. So I think that we have a pretty good picture of the physical world with quantum mechanics. We don't know very much about mind. We don't know, for example, what, even aside from this crazy picture I outlined, just we don't know why this laptop doesn't have consciousness and a mouse does, assuming that they do. We don't understand why certain physical structures have consciousness associated with them and others don't. We don't really understand anything about that. But presumably there are some laws, but I think consciousness is a natural phenomenon. I think there are natural laws governing all of that. There's some laws of nature that say this doesn't have consciousness. And there's some law of nature that says, that implies that a mouse does, okay? Now, we don't know anything about those laws, but presumably those laws specify what kinds of physical structures have consciousness and what don't. And I agree that there's this whole question of a basis problem and how you...
My question is really about...
It's really mind, whatever those psychophysical laws are, says recognize this structure in this branch that is decohered. This structure is the kind of thing that can have a mind, and it does have a mind, and so do all the other. And so the work done, something else in my ontology, mind is a part of my ontology, consciousness, and there are laws governing that which we don't know anything about, though I would claim the Born rule is like one little piece of that. But that would do the work picking out. So if your branch only had, laptop computers in it, there won't be any consciousness in it. But if your branch has something resembling a living mouse with a functioning brain, then it would have consciousness. But that would be determined by these other laws of nature that we don't know.
Maybe one more short question, Fernanda?
Well, you know that I am one of those physicists that speak of the mind as if it has nothing to do with anything, or rather I don't.
You're a materialist.
But I always fascinating whenever I ask questions about this. So I don't know if this is what Vincenzo was going towards, but this last statement almost gives me a flavor of a change in like coordinate system or something like that. Oh, before that.
No, I just forgot to put up these slides.
In coordinate systems, when you've moved the collapse of the wave function and the original problem of the probabilities into whatever it is that makes the consciousness.
Right. Where's the question?
In one branch. Is that, well, one is if that's kind of correct, but the other one is fundamentally the link that takes you to postulate that this has anything to do with consciousness. Is that where is that?
That was earlier in the talk. Before I got to the crazy part.
Well, nobody believed that before Wigner.
That's not true. You can find old books. I mean, there's a book I saw by. Wait a minute. Hold on. Let me answer you. There's an old book goes back quite a ways. I found in the physics library by Sir James Jeans, long before Wigner was saying anything about this. And he's called them knowledge waves. Waves of knowledge. I mean, the idea that this quantum mechanics had something to do with the knowledge of observers goes way back to the 1930s. So it's not just something that Wigner started talking about out of the blue. In fact, he said, I'm telling you what people have traditionally thought.
I misspoke. I meant it's not necessary to the theory. So if the connection is in the knowledge, is there some sort of counter argument to be made, or how would you respond to the argument that the knowledge of what was the outcome of the collapse does not exist before it? So like you said something like...
Yeah, of course, the knowledge of the outcome can't exist before the outcome unless God supernaturally reveals to somebody what the outcome of his experiment is going to be.
Like it's a lack of knowledge that you...
But anyway, we can talk in private. This sounds like you want me to explain in more detail. And that's not something I can do in a very brief manner. But I would like Father Ambrose to ask a question.
Well, I mean, I did find some people who have similar views on this, if you want. But so you have the minds that are going along one particular branch, but there are also things that are in that branch that like don't have minds. So say
most things.
Most things, that's right. So like what would be the difference in the way that you calculate over the formula, you calculate over like something like a block of marble in the branch with mines, as opposed to could you make a calculation, or would there be a different type of change in the thing in the non?
Outcome of the experiment?
Yes, so like
There's no difference. No.
So then you're calculating whether the spin is going to be up or spin is going to be down, or the beam's going to go this way, the beam's going to go that way. You generally don't in real life. And then calculate everything that happens thereafter when the particle that went up into your detector interacted with all the Avogadro's number of particles, and you don't, and then worry about whether. One problem that might come from this is, while you've eliminated the possibility of there being an infinite number of like me and other worlds, right? You've not eliminated the possibility that there are an infinite number of like Michelangelo's Davids.
Oh no, there are. I mean, to the extent you attribute reality to those worlds, that those Davids will not be appreciated aesthetically by anybody, because there won't be any minds contemplating them and experiencing them.
Okay.
So, I mean, as I said, if you're sort of Berkeleyan, you say, well, those are just sort of shadowy things that have a mathematical existence, but not a real one. But I mean, yeah, there'd be blocks of David and everything else and all this, but there just won't be a living, well, maybe breathing, but there won't be a conscious thinking Father Ambrose Little in those other branches. You may be reassured to know. Doing God knows what.
Now for further discussion, let's thank Dr. Farragut. Reminder, Father Matthew will be offering Mass in traditional Latin form around 5:30, something like that. So now we turn it over to Vincenzo. Yeah.
So.
Single function. There are many ways to this. So the function collapses for one observable, but the other observable still has another. That's why
AI. I think that's what my theory solves. My theory solves that.
Well, you're thinking in writing this.
Unfortunately not. I mean, I have it in some writing, but it's not ready for prime time.
I just want to thank the speaker of the session of today. So we forgot to thank everybody. It's a wonderful session today and very nice talk. We have few minutes per and just a smaller session with the speakers for I guess 45 minutes. So and then we will go beyond the TLM on we will start maybe 5:30 to 5:55 or something. Yes. So thank you everyone for being in this room. We start in 2 minutes or so. So because just so for all the speakers.